Am I audible?
Yes, sir.
Yeah, clearly, sir.
Yes, sir. Audible, sir.
Yes, audible, sir.
Very good evening to all the distinguished guests, respected speakers, estimated faculty members, and all my dear participants. I am Dr. Madgonda K. Biradar, working as an assistant professor in the Department of Mechanical Engineering and also coordinator of this Atal FDP. It is a great privilege on the behalf of Mechanical Department of Nutan Maharashtra Institute of Engineering and Technology, Talegaon Dabade, under the umbrella of Nutan Maharashtra Vidya Prasarak Mandal and the Pimpri Chinchwad Education Trust. I would like to thank our beloved CEO, Dr. R.S. Jahagirdar sir, and also the principal, Dr. S.N. Sapali sir, for supporting us continuously to conduct this FDP very smoothly. They are the backbone for our FDP. Thank both of them. Again, I would like to thank Head of the Department, Dr. Satish More, and the coordinator of this FDP. Thank you, sir. I would like to thank to AICT as well as the Atal officials to scrutinizing our applications and giving the chance to organize this FDP for all the faculty and the industry fraternity. I welcome you all for this 6 days online Atal FDP under the title of Industry 4.0 in Energy Sustainability. ऑफिस में है अब चले गए sorry for inconvenience. As we know, the fourth industry revolution, that we call it as a industry 4.0. Am I audible, sir? Which
Yes,
is
you are
not a
audible.
revolution of the.
Yes, sir, you are audible, sir.
Thank you, sir. As we know, the fourth industrial revolution, that we call it as a industry 4.0, is not just a evolution of the technology, but a revolution in how we approach the production, energy use, and the resource sustainability. As we all know, the modern world, which is facing the unparalleled challenges, including the climate change, then the resource depletions, and the urgent need of the sustainable energy sources. These challenges demand the innovation and the innovative solutions at the irrespective of the intersection of the technology, policy, and the human collaborations like we all. The focus of today's program, which is leveraging the Industry 4.0 technologies to promote energy sustainability and tackle the climate change which is happening around the world. The convergence of IoT as well as the artificial intelligence, then the big data, automation, and the digitalization, which is enabling the industries to optimize their process, reduce the energy consumption, and minimize the environmental impacts. By empowering all these smart manufacturing systems and also the predictive analytics and the data-driven decision makings, the industries are increasing their efficiency as well as they are able to operate in a ways that are both economically viable and environmentally responsible. Moreover, these technologies can drive the circular economy as well. It should reduce the carbon footprint also and ensure that energy systems are not just efficient, but also they are the resilient to growing the impact of climate change. As we gather here for this FDP, we have a unique opportunity to gain the deeper understanding regarding the Industry 4.0 in energy sustainability and climate change, which can be applied across the various sectors to promote the energy efficiency, support the green energy initiatives, and also to mitigate the harmful effects of climate change. Throughout this program, you will be introduced to innovative concepts, case studies, as well as the best practices which are showcasing around the world to reduce the carbon footprint and to balance the ecological system. Also, we will understand how the integration of advanced technology is transferring the industry and creating the more sustainable future. I would like to make emphasize the improvement and the importance of the collaboration in the endeavor. As we are the researchers, technologists, we should have the collaboration in our work. The shift of the sustainable energy future requires the cross sector operating among the industries, researchers, policymakers, and the different communities like we all are gathered here. It is essential for the academic and the industrial leaders like we to not only the deepen in the knowledge which we are gaining from these type of the FDP or the STTPs, but also build the bridge or the gap between the economy as well as the society, and which we shared in the learning. I'm confident that this program will not only enhance our academic and the professional expertise, but will also inspire us to contribute to a technological advancement that supports the sustainable development goals and also the affordable and the clean energy along with the climate change. So before I conclude, I would like to express my sincere gratitude to our organizing committee, our esteemed speakers, and all the participants, and the head of the institute, Principal Sir, Dr. S.N. Sapali Sir, and CEO, Dr. R.S. Jahagirdar Sir, making the successful begin, or we can say is the best begin is the half done. So we are here. All the participants, your dedications and the advancing the knowledge of this FDP under the title of Industry 4.0 in sustainability, energy, and the climate change, which is really commendable. You have showed your interest to attend this FDP. Definitely, it will add on to your life as well as your research work. Let us embrace this opportunity to learn, innovate, and collaborate in creating a more sustainable and resilient world. I wish you all successful and enriching learning experience through this FDP. Thank you all. Now, I would like to request Dr. Satish More, coordinator of this FDP, to share views and the information regarding the department.
Thank you, sir. Good evening, one and all. Respected Dr. S.N. Sapali, Principal, Nutan Maharashtra Institute of Engineering and Technology, Talegaon. Respected Dr. R.S. Jahagirdar, CEO, Nutan Maharashtra Institute of Engineering and Technology, Talegaon. Respected Dr. Aparna Pandey, Principal, NCER, Talegaon. Distinguished guests, respected speakers, esteemed faculty members, and my dear participants. I am Dr. Satish More, Associate Professor and Head of the Department, Mechanical Engineering, Nutan Maharashtra Institute of Engineering Technology, Talegaon, and the coordinator for today's FDP. It is my absolute pleasure to welcome you all to 6-day Atal Online Faculty Development Program on Industry 4.0 in Energy, Sustainability, and Climate Change. on a special occasion that brings us together to celebrate, learn, and connect. On behalf of Mechanical Engineering Department and Nutan Maharashtra Institute of Engineering and Technology, Talegaon, and FDP organizing team, I extend a warm welcome to all our distinguished guests, speakers, participants, and attendees. Your presence here today reflects your enthusiasm and commitment to contribute to society related to technology, energy, and the sustainability. Department of Mechanical Engineering was established in 2012. Department is accredited by NBA in 2023 for the 3 academic year. Currently, department is having 120 intake. 5 faculty members are the doctorate from the NITs and IITs in the Mechanical Engineering Department. Now, we are honored to have a well-known speaker, expert from the various fields like academic, industry, and entrepreneur. Dr. Yadav from IIT Patna, Dr. CP Paul from RRCAT Indore, Dr. Kumar from NIT Surathkal, Dr. Ajay Chandak, entrepreneur, Dr. Sudeep and Mr. Vilas Tiwai from USA industry, and many for joining us. Your participation had immense value to this event, and we look forward to your insight. We are great response from the participants. Now, total participants are 186 registered to the Atal portal. Participants are not only from Maharashtra, the participants are Gujarat, Tamil Nadu, Rajasthan, Hyderabad, Karnataka, Uttar Pradesh, Madhya Pradesh, and etc. FDP topic is related to Industry 4.0, energy sustainability, and climate. It's applicable to each and every one for all the fields and areas. Therefore, we are having the participation response from the various fields like mechanical engineering, EITC engineering, environmental engineering, civil engineering, production, food science, technology, computer, IT, etc. Our program has carefully crafted and ensure both the engaging and joyful for the everyone. As we embark on this journey together, I encourage you to participate fully, share your thoughts, and make the most of this opportunity to learn from and connect to one another. Once again, thank you for being here. Let us make this event memorable one. Thank you. Thank you, sir.
Thank you, sir. Now, just in briefly, I introduce our beloved principal, Dr. S.N. Sapali, sir. Sir is currently heading as a principal at Nutan Maharashtra Institute of Engineering and Technology. He also worked as a professor in a Department of Mechanical Engineering at COEP Pune. He worked as a Dean Quality and Assurance from 2019 to 22. Also, he served as a head of the department more than 5 years. He was the one of the first IIIT registrar at a Pune. Sir qualified BE in Mechanical, PG in ME Mechanical, and PhD from the IIT Kharagpur. Sir has held the different posts as a lecturer, assistant professor, and the professor at various institutes. He is having more than 36 years of experience in an industry along with the academy. Sir is having the infra creation achievements. So he has renowned the mechanical department during the headship of around 4.5 crores through the sponsorship of the Bajaj Automotive Limited. Sir has guided more than 14 students for the PhD and 3 are going on, and he has guided MTech students more than 50. Sir is having the reputed national and international papers more than 125. He is having the 9 books on his name as an author, including the refrigeration and the air conditioning by PHI Learning. So he has trained more than 500 faculty members in a refrigeration and air conditioning through the more than 10 FDPs. Sir has given the expert talks at a different places. More than 100 places he has given the expert talks as a keynote speaker. He is having the he has totally filed the 9 patents. Out of that, he is having the 4 patent grants on his name. Sir has developed 3 products, including the portable AC, new air cooler, and the transportable jaggery plants. He is having the more than 13 awards, national as well as the state level, including the best teacher awards also. He has completed 5 research projects with almost
Doctor,
95 lakhs.
doctor, enough.
Okay. And he has almost consulted the different agencies, more than 42 crores, the worth of 42 crores. So if I talk regarding the Dr. S.N. Sapali sir, below
Conclude.
principal, the list will be more. So, sir, I welcome you, sir. I request you to address the gather and give your sightful for this FDP, sir.
Thank you, Dr. Madgonda, for your
Thank
brief introduction. So, first of all, I congratulate the coordinator, Dr. Madgonda Biradar, and Dr. Satish More, Head of the Department, Mechanical Engineering, Nutan Maharashtra Institute of Engineering and Technology, for getting this sanction from AICTE, New Delhi. It's a great achievement, actually. Normally, so people get, if 100 applications are there with AICTE, only 10 people or 15 people are going to get out of 100. So like that, they are really done a good job. And I'm also thankful to Professor Dr. Biradar, Jahagirdar sir, CEO of this institute, being guiding, creating a good infrastructure facilities in NMIET Pune. Then looking at the topic, so I pronounce like this, it is Industry 4.0 in energy sustainability and climate change, actually. So industry 1.0, 2.0, 3.0, 4.0, like that. I think it is industry 4.0 in the energy sustainability and climate change. If I'm wrong, you may correct me. So I'm also thankful to all the experts from all over the world. So those are going to participate and share their rich knowledge in their specialized field and all related to this sustainability and energy. So going ahead with, actually, our government of India has signed an MOU at international level, so making zero emissions by 2047. So therefore, in line with that, this topic sanctioned is very relevant, actually. So as far as energy is concerned, there are only two divisions, you can say: energy generation devices, energy consuming devices. So as far as the energy generating devices are concerned, maybe thermal power stations, solar power stations, etc. They are operating at a highest level of efficiency at this stage. Then coming to the energy consuming devices, especially electronic devices, refrigeration and air conditioning devices, and pumps, compressors, etc. There is a need to improve their performance, means reduce the energy consumption for the equipment, these what you can say, machinery is designed for, actually. So if we do like that, so then there will be reduction in the emissions of CO2. Now let us take one example. So if we consume 1 electrical unit of energy, so to generate this 1 electrical unit of energy, how much how much coal is to be burnt? If we consider thermal power stations, almost 600 to 700 grams of coal is to be burned to generate 1 unit of electrical energy. Then how much carbon dioxide is emitted in the atmosphere for 1 what you can say, electrical energy unit generation through use of coal? So it is almost 2.2 odd kg of carbon dioxide is emitted. Now imagine how many vehicles are there on the road, what is the power generation capacity of the thermal power stations, in what way per second how many kg of CO2 is being emitted to the being added to the atmosphere. So therefore, adding such a huge amount of carbon dioxide into the atmosphere, so the global warming is what you can say, change in the climate, so change in the what you can say seasons like rainy season, winter season, and summer season, everything is being changed. Change is happening, lot of disturbance is created. So therefore, to save this earth, so we have to go for energy efficient, or we have to reduce the carbon dioxide emissions in the atmosphere. So therefore, this topic is very much relevant, and speakers are going to add in their field. So I appeal every faculty, so attendant participants, so attend the course fully, is very useful, and take away with them what they can learn from this, what you can say, such a wonderful, what you can say, Industry 4.0 in energy sustainability and climate change, organized by Dr. Satish More and Dr. Madgonda Biradar. So with this, I take a leave. I wish you all the best of luck ahead for the next 6 days. Thank you. Thank you all.
Thank you very much, sir, for your insights for this FDP. Definitely, just I want to add the thing. Sir is from the thermal background, so he is having the vast experience in the refrigeration, air conditioning, as well as all the thermal related. So definitely, sir, this FDP will help to all the participants. So definitely, will make the more knowledgeable, sir. Now, thank you, sir. Now, this is time to briefly introduce our CEO, Dr. R.S. Jahagirdar, sir. Sir, he is having the tagline of, everyone will have the tagline. Sir is having the tagline, that is, develop yourself, the nation and the institute will automatically develop. So one of the young and energetic CEO, which we are like a witness for the Nutan Maharashtra Institute of Engineering and Technology. Sir is having the more than 39 years of experience, along with the 6 years of industry and 33 years of teaching. And he served as a more than 21 years as a principal to the various reputed institutes. Currently, sir is heading as a CEO at NMIET. Sir has completed his PhD from SRT Marathwada University and his graduation from the NIT Jamshedpur in 1983. So sir is having the, means he has guided more than 10 research scholars for the PhD. And sir is really, I would like to say, he is the mastermind for the getting the NAC and NBA to get accredited, how it is efficient, means it is efficiently how we can work for the NAC and NBA. Sir has worked as a evaluation director at a different level of the institutes, even to the University of Bamu. He worked as a BOS, academic council members, finance committee member, and even the management
let
members.
us cut short, sir. Cut short.
Definitely, sir. Sir is having the more than 10 major projects, and he is having the number of patents on his name. It is not only the filed, these are the granted patents. So again, as I said earlier, like sir is again the master in the thermal field. So he is more related to this sustainability and the climate change along with the energy. Sir, I welcome you, sir, for this FDP. I request you to enlighten regarding this FDP, sir.
Yes. Thank you. Good evening, everyone.
Good evening, sir.
My heartily congratulations to the Biradar sir and the More sir for organizing such an excellent FDP on the topic which is having the more concern and more awareness is to be developed among the society. And we as a teaching community is the one who can develop and who can increase the awareness among the students, among the all stakeholders, and also these students who will be the working for tomorrow as the working professionals, maybe in the industry, maybe in the government organization. This will help to enhance, or rather I can say that the maybe 2047, which is our limit, that maybe we can prepone by a year or so. That is what actually we are looking. Now, when we say about the Industrial Revolution 4.0, particularly when I started working in the industry, it was the 2.0. So I know I have seen, I have witnessed how much development and how much efficiency has increased right in the production, right in the manufacturing, in the maintenance. Nowadays also the maintenance. We are not going for the continuous maintenance, but we are trying to replace the technology with the latest one. And here, from these speakers you are invited, really they are eminents in the field. And my appeal to all the faculty members particularly, please listen it carefully, try to inculcate what you have studied and communicate and give these messages to the students or wherever you are going for this, addressing the gathering. Uh, Convey this message that we are looking for the sustainable development. Sustainable development is the one buzzword nowadays, which we as a faculty should incorporate in our life. And I'm sure that after this FDP, you will inculcate, you will add this word in your buzzword and also in the keyword. As normally in the research paper, we say the keyword. So my appeal to all, add this as a keyword and make it happen to your students. All my best wishes to you, sir, for your FDP. Thank you.
Thank you very much, sir, for guiding us for this FDP. Definitely, sir. We all the participants will take your words. So we'll work with the Industry 4.0 with the energy and efficient energy and climate changes, sir. Thank you. Thank you very much, sir.
Dear participants, we are having the first session at 6:30. So we will take some 5 minutes break. After 5 minutes, we'll again come back. So the link is same. We are not going to close the link. So everyone is joined after 5 minutes. Experts will join within 2 or 3 minutes. So we will exactly start after 6:35. Thank you.
So here we conclude the end of the inauguration. Thank you very much, our CEO sir, and the principal sir, Dr. Sapali sir, and also the Dr. Aparna Pandey, principal, Nutan College of Engineering and Research, and all the participants. You all have shown your interest to attend this FDP. Definitely, because of your interest, we could reach more than 185 participants for this FDP. So it is really a very big thing. So thank you all. So within 5 minutes, we'll start with the first session. We have the eminent speakers. So just take a break for 5 minutes.
Yeah, Madhu, can you hear me?
Yes, sir. Your voice is audible, sir.
Okay, thank you.
Thank you. Sir, just you can share your screen, sir.
Yeah, Madhu,
Yes, sir. It is visible, sir.
it is visible, my PPT?
Yes, sir. Yes, sir.
Okay.
Yes, sir. Yes. Welcome back, all participants. Now we start our online Atal FDP with the first session with the most young and energetic speaker, Dr. Ajay Kumar Yadav. Sir is working as associate professor in the Department of Mechanical Engineering at IIT Patna. Sir has received his MTech and PhD degree from Indian Institute of Technology, IIT Kharagpur in 2008 and 2013. He joined the Department of Mechanical Engineering at IIT Patna in 2022 as associate professor. So before joining to the IIT Patna, he has worked as an assistant professor in the Department of Mechanical Engineering at National Institute of Technology Karnataka Surathkal, which is NITK Surathkal, Mangalore in Karnataka from 2009. His area of research includes supercritical fluids, heat transfer, CFD, bioheat transfer, solar energy, IC engines, refrigeration and air conditioning. The list goes on. He has published more than 100 research articles in reputed international journals and also in conferences. He has supervised 9 PhD students and more than 25 plus MTech students. And he has received 6 sponsored projects under the various funding agencies such as DST, SERV, PGST, etc. Those are having like a fast track projects which are funding of more than 25 lakh. He is having the DST project which is funding of more than 30 lakh rupees. Imprint 2 project from the MHRD New Delhi, which is funding of almost 49 lakh rupees. He is having the funding from the SERV for the solar energy purpose. And again, from the SERV, he got the 15 lakh funding for the design and development of supercritical carbon dioxide based natural circulated solar thermal collector. Also, he got the funding from the VGST Karnataka for the project of development of ternary mixture based vapor absorption system, which is fund of 15 lakh rupees. Sir is having, like, he is an expert in writing the proposals and getting the fundings from the different agencies. So if any participants require the more information or the like a knowledge regarding the how to get the how to write the proposals and fundings, from the central and the state governments, definitely you can reach to this, sir. So, sir, before joining to the NITK, so he served as a served in the Indian Navy for a 7 year. So we have witnessed he is having the punctuality and the sincereness, so which is came from the Indian Navy, and he worked as a junior engineer in a Indian Navy as well as in a different levels, and also he worked in the steam power plant, gas turbines, refrigerations, and air conditionings, along with the pumps and the compressor. So before that, sir worked in a ISAR also. Sir is having the all combination of the industrial as well as the teaching experience. So we are very fortunate to have such a speaker with us, so that we will make all this session very fruitful. I welcome you, sir.
Thank you, Madhu, for nice
Thank you, sir.
introduction. This much detailed introduction was not needed. Just a few lines was sufficient.
Thank you, sir.
Okay, so what is next? Shall I start?
Yes, sir. Yes, sir.
Okay, so here, yeah, good evening to all of you. This FDP, I think now planned in the evening. Maybe you all are available in the evening. Daytime, you'll be busy in teaching. So this is good, also good initiative. Here, I hope most of the participants are from thermal background, I think, or different backgrounds. Madhu?
Yes, sir. It's a combination of all, sir.
Okay, so it is combination of all, so we'll not go in more details, more depth of the research. Okay, so that's why I wanted to know. So, okay, we will, I'll try to cover as much. Let me share the screen. Okay. So now I think my screen is visible to all of you.
Yes, sir.
Yeah, right?
Yes, sir. It is visible, sir.
So this FDP is on sustainability, renewable energy, like that, this type of subject. And this is one of the important one. Topic is solar energy. What are the recent developments in solar air heater today? This is the topic. I'll talk on this solar air heater. So mainly on this, I'll talk on the two broad area here. Study of means my research part. I will talk study of triangular duct solar air heaters with V ribs as artificial roughness, and another one is solar air heater with semi-cylindrical sidewalls. But these two area we'll talk the later part. Before we'll talk about the introduction, because these things will go in research part mainly, because all are not from thermal background. So I will go little bit, I'll explain on that. But the detailed introduction and this thing will be interesting for all of you. In this, I'll go through the what are the different types of solar collectors, classifications, and this artificial roughness in a solar air heaters. See the solar air heaters in the application. I'll talk about the solar air heaters. What are the applications? And different duct cross sections. The things what I'm going to talk here is one is artificial roughness in solar air heater. Why this is required? Duct cross sections. Then how to solve this solution approach. In that numerical and experimental, mainly we'll talk about the different softwares people are using or writing codes. Then some results and discussion part and conclusion. And this is the very common things why we go towards the renewable energy side. The thing is, one major part is the pollution part. We burn fossil fuels, coal and gasoline, diesel. So this one thing is it is creating pollution. Another thing is there is a depleting the source. So availability is also question mark after a few years. So the thing is we have to move towards the renewable energy side. And sun is the better option always. But so how much we can harness from the sun, that matters now. So how to increase the efficiency, those things we should think of. So one thing is, why not photovoltaic? Photovoltaic cell, the thing is efficiency is very less. You know that photovoltaic cell is having efficiency of around 15 to 20%. Okay. 15% generally you can consider 15 to 18% in this range. So efficiency part is we need to work on that, and we have to increase the efficiency. Other part, if you talk about the thermal part, thermal collector part. Thermal collector, if you talk about water heater, solar water heater. So solar water heater is having efficiency of around 60 to 70%. So you can think where we are getting 15% in photovoltaic and here we are getting 70%. This much difference is there. So if you have the application of heating applications, if you want hot water, then you don't take use the photovoltaic, then take that electrical energy from that, and electrical energy use electrical heater and do that. You are not going to get more than 15%. So it is 15% the collector efficiency, then heater, some losses will be there. So the thing is, if you need direct electrical energy, you have the application of direct electrical energy, then PV cell is good. Otherwise, if you have the application of heating purpose, then don't go to that side, PV cell side. Here it is better option, 70% you are getting. So this is the water heater efficiency, you will get around 70%. In that also, again, I'll talk details on that also. If you increase temperature, efficiency will drop. But it won't go less than 50. Generally, it will be above that. Okay. But if you come to the, this is the introduction part. First, let me talk about the global warming and all things. It is better to go for solar. Okay. So it is expected to increase 2 degrees Celsius by 2050, this temperature, ambient temperature, global ambient temperature. So these are the things, and escalation of price is even higher than the inflation rate, that fossil fuels, that conventional sources of energy. So this is the one motivation why we are going towards solar energy. And this is the temperature of the surface, global surface temperature. You can see this, the range from 1880 to 2020. It is around 2 degree change here. So these are the data generally we can get from some reports are there in that. So like in India, gross petroleum import, how much is there? Okay, so accounted for over 2020 to 21, that is for 1 year, this data I'm presenting here, accounted for over 19% of India's total imports. So, and coal also, India is the second largest importer of coal. So these are the things you can see how much we need fossil fuel to fulfill our energy demand. So, and solar energy part, solar air heater, what we are going to talk, the major application of the solar air heater part is in the food industry, drying the food product. This, if you see, you can see here application of solar air heater. Hot air from the solar air heater can be used for various low to medium temperature application. Okay, mainly drying of agricultural products. So for a developing nation, these are the where agriculture farms, because these countries, you know, the mainly the agriculture based. So agriculture farms, the economy is backbone. Drying and preserving farm harvest is of prime importance. So in that there are indirect type solar air heater, direct type solar air heater. There are different types. Okay, we can use. And another use of the solar air heater is space heating of buildings. So in a winter season, you need hot air. If you use solar, normal PV cell and electrical heater, if you use, mainly in the north side, very cold environment, you need heater. So that consumes a lot of energy. Directly, if you use a space heater, solar-based system, so you will get around 70% here, not 70% you will get, because air heater has less efficiency than water heater. Okay, so water has a better conductivity than air. So if you use, even if you get 60%, 50% efficiency, that is much better than the 15% of the photovoltaic cell. So these are the things, space heating you can use. Then industrial application, process heat requirements, solar cooling and air conditioning, seawater distillation. Okay, solar steel you might have heard. So that purpose also you can use this solar air heater. Now different types of solar collectors I will talk. Okay, what are the different types of solar collectors? Mainly thermal collector. What I'm talking here, solar thermal collector I'm talking, not the photovoltaic. Photovoltaic is totally different. This is supercritical CO2 based flat plate collector. First one which we built with Biradar in his during his PhD. Other things are, this is solar water heater, evacuated tube solar water heater. So this is widely used water heating purpose. Supercritical CO2 is actually my research area. So in this, this has very high efficiency, but there is a risk also. It works at very high pressure, around 90 bar pressure. Okay, so very high pressure it works. Parabolic trough collector and dish type collectors. So these are the things. What we do here, if you need high temperature, you need such type of concentrated collectors. Okay, so this is parabolic and this is dish type. Dish type, if you use for water, you can go up to 800, 900 degrees Celsius in that range. To run like a power plant, a thermal power plant, if you want to run, you can go for this. Okay, so the thing is, people have tried that also, solar thermal power plant. Okay, some places it is running. But the thing is, as you go higher and higher temperature, there's a losses also. Efficiency of the solar collector will drop. So one thing is, here you are using free of cost, but efficiency matters because the photovoltaic cell is better. There's easy to handle. Here you need collector part, then turbine part, so then generator. Many things are there. Moving components will be there. So initial cost will be very high if you use thermal power, solar thermal power plant. And efficiency also, it may come close to that 20-25% in that range. So you can see the maximum temperature, how much you can get using flat plate, evacuated tube, parabolic, and dish. So this 80, 180, 400, 900 degrees Celsius you can go. So as you increase temperature, your efficiency will drop. That is the main drawback here. So let us see this. You can see with the effect of temperature on efficiency. You can see if it is, you can see here it is around 72 or 73% efficiency you are getting. On the higher side at 100 degrees Celsius. As you go 400 around, you can think you are going to up to 55 degrees Celsius. So if you need higher, if you need fluid at higher temperature, so if very high temperature, then efficiency will drop and may not be suitable at very high temperature. So the normal range 100 degree to 100 degrees Celsius is good to use this solar corrector, thermal corrector. Now the thing is, I'll talk about the flat plate solar air heater. So solar air heater is generally, if you see this solar air heater will be like this. Simple, very simple in construction. It is making this solar air heater is very easy. Okay. So in that, what is this is a glass part. Solar radiation will be absorbed here, and you can see the cross-sectional view or side view. You can see here. So this will be on the top one is the transparent glass cover, and this is the absorber plate. This one. And in between, you can create vacuum. There are different types of solar air heater in this also. Class 1, class 2, class 3 types. Okay. So some places vacuum is not there. Okay. So if you use vacuum, the losses will be less. Okay. So this is the normal construction. You can say this is the simple side walls. This will be insulated. Okay. Here air will flow in between this part. So you can see here the classification of flat plate solar air heater. This one is the transparent cover. This is, you can say, the glass. This one is the glass, and this is the insulation, bottom insulation, and in between, and the insulation is this side, but here in the top of the insulation, this is the absorber plate. Okay, which will absorb the solar radiation here. Okay, and this will be generally black chrome coated. So you know the black body accepts all the radiation, so it will absorb. The absorptivity will be more or close to 100%. So here this plate will get heated. Absorber plate will get heated, and here in between this glass and absorber plate there will be airflow. So when air will flow, this air will take heat from this absorber. Okay, and this air will get heated, and it will pass through this, and after this outlet air you can use for your application. So you can send this air for drying the food products, agriculture product. So this is the class 1. This is type 1, you can say, type 1 flat plate solar air heater. Type 2, what you can do here, this is the absorber plate in between. You can see this. This is the insulation here. Here absorber plate. Here it is dashed line is transparent cover, the glass, and you can pass air from both sides. So both area of this absorber plate you can use, top and bottom side, both side you can use, and air will flow through this. So you can extract more heat, you can say here, okay, in this way. So this is called type 2 solar flat plate solar air heater. Then this is the third type. Here you can see the transparent cover, glass, dashed line, and then this is absorber plate. So in between there will be vacuum. Actually the big problem is here the losses. Losses, absorber plate and air. So with the air there will be convection here, and with that convection, there will be losses to the air to the transparent cover glass and glass to the atmosphere outside. That loss will be there. So to minimize that loss, you can create vacuum here. So there won't be any convection in between. There's a vacuum, so no air, means very less air you can say, try to create high vacuum. So that convection losses will be less, or you can say zero almost. So this one, this air, you can see here, air is flowing between the absorber plate and insulation. Insulating material is here. In between it is flowing. So this is the three different types of solar air heater. Now, in this, the solar air heater has a low efficiency compared to water heater. The reason is the air has very low thermal conductivity. This is a one major main reason here. So how to improve the efficiency? We need to put some, how will improve? You have to improve the heat transfer coefficient. So heat transfer coefficient will be always higher in the case of turbulent flow. So you have to put artificial roughness here to create turbulence in that. Okay. So how to put that? The thing is, if you are just the smooth normal channel, okay, and air is flowing in that, there will be boundary layer will be created on the flat absorber plate. So once boundary layer is created there, developed, then that heat transfer rate will reduce it. At leading edge, you know that at the leading edge where the plate starts, you can say, and flow is coming. So that is the leading edge. At leading edge, always heat transfer rate is very high. So that concept we have to think and implement here, so that we should break the boundary layer. And again, first break, because a thick boundary layer will be formed, so that we need to break it. And in that, even the boundary layer, there will be laminar sublayer will be formed. So laminar sublayer, in that actually the up to the thickness of the laminar sublayer, you have to put this artificial roughness, some fins like structure in that. Okay. So if you put some restrictions like fins type of structure in that to create the artificial roughness, there will be pressure drop. You need to use higher or bigger size pump in that. So pumping loss will be there more. One side you are getting higher Nusselt number or heat transfer coefficient, other side you are getting higher pressure drop also. So these two things are there, and you have to get the optimum parameter with this. So let me, okay. So next page you can see this. These are the different types of finned plate. This is a finned plate, a different way of creating this artificial roughness in that. You can see first one is you are putting fin in this absorber plate. Okay. Second one is corrugated type we are putting here, so that you can get some turbulence in this. Now the thing is, if you are putting this ribs in that, like fins type of a structure here, putting, there will be pressure drop and Nusselt number will increase, heat transfer coefficient will increase. And two things, one is increasing, another is pump power is also increasing. So one is favorable, Nusselt number increasing is the favorable condition, but friction pressure, friction coefficient is increasing. That is not favorable condition. So there is a parameters that is called thermohydraulic performance parameter. So that one relation is there. So how much Nusselt number is increasing? Nusselt number is mainly representing the heat transfer coefficient, and other part is how much pressure drop is increasing. That ratio of these two, there's a relation. One actually, it is not direct ratio. There's a relation in these two, and that will say whether it is more than one. If it should be more than one, otherwise that is not justified to use. So it should be more than one, so that we will evaluate. Actually, for all types of, even whatever you use, any system where the heat transfer you want to enhance, you have to see that how much pressure drop is increasing. So these two ratio you have to always see, and you have that the parameter which will give you the these two comparison is the thermohydraulic performance. So in that now we will see the different types of ribs we can use, that fins type of structure. Ribs we can use, and what is the criteria to use that. Okay. So one thing is here, impact of rib height on the flow pattern. What is this actually? Rib, this is very small diameter. You can say that this is 1 mm like that. Okay. E1, E2, E3, 1 mm, 2 mm. And flow is from left to right. You can see the flow direction here. Left to right, it's going. Okay. So, and this is 1 mm, 2 mm, and the around the height of channel will be very large. Okay. So this is actually, this roughness height should be of the order of laminar sublayer. You have to break that. And again, it will form, like you can see here, this, it is coming from this side, and here it is, you can see reattachment occurring here. So you are breaking this sublayer, laminar sublayer, and again reattachment is happening here, again forming the bond layer here. So this reattachment point, you will get highest heat transfer coefficient, where it is getting reattached, flow is getting reattached here. So this part we have to see. So what should be the height of this rib height, that how to decide? You can do the analysis and do that, get the result. So here what we have done some literature and our own study, what we found here, relative rib height corresponding to maximum heat transfer for different ribs in the SH, solar air heater, is around 0.03 to 0.0. Okay, so this is RH value. RH is what? E by D. D is hydraulic diameter. Okay, so this is the ratio. E by D is 0.03. So around how much? You can see around 30 times. So with this, if it is of 2 mm, then 30 times you can say 60 mm will be the height of the channel. So the thing is, you have to see this. If you are putting directly, blindly, without doing any study, and putting these ribs of different height, you will find that this one, you can see the fourth case. Even from the third case or fourth case, there is no use of putting this. Okay. Because there is no reattachment. So if there is no reattachment, you will not get that heat transfer coefficient, higher heat transfer coefficient. Okay. No use of putting this. Similar way, if you see the pitch, means how much distance you should put. One you have put here, another one how much distance you should put. That is called pitch. Okay, so 1, 2, 3 you will put in that, and flow direction is here. So this distance you can see, if you go on decreasing the distance, okay, this pitch distance, you can see here reattachment is happening here, first and second, you can see third also, you can see here fourth one, because it is very close. So if you are putting very close, means you can say relative rib pitch. What is this relative rib pitch? Here is P by E. E is the height of or diameter of one rib, you can say diameter if it is circular, otherwise you can say the height. So P by E is like this, so 8 times. So this height is suppose 1 mm, then 8 mm it should be difference between these two ribs. If you are putting in this range, then you will get the reattachment, otherwise you are not getting. You should put it more than that. 9 to 15 we have put here. So 8 or below 8, rarely you will get. That depends on the different types of flow also, but the chances of getting reattachment is less if it is less than 8. So it should be more than 9 to 15 in this range. So there are other parameters also which will affect this 9 to 15 what I wrote. Just this is the approx value. Now the thing is impact of rib inclination on the flow pattern. If you are these ribs, you can see this will be a small diameter, 1 mm, 2 mm in this range. So if this you can put perpendicular to the flow direction. So if you put perpendicular to the flow, transverse direction, then there will be here some vortex will generate. Okay. And stagnant type of region will be here. And behind that also, behind this rib. So that we don't want that actually. So how to avoid that? So if you put at some angle, what will happen? If it is at some angle, what is the flow is coming here, there will be secondary flow. This red color you can see here. There will be secondary flow which will flow along this rib, this direction. Along this rib, and this, if it is flowing along the rib, what will happen? This fluid will take heat from the plate, okay, and this will mix with the main flow. So you will get some amount of heat out from the collector plate. So this way it will increase the efficiency if you tilt it. So this tilting angle varies, depends on the configurations. It may go to 45 or 60 like that. Depends on the configurations. Okay. Now the thing is the impact of rib cross sections. What I showed you earlier in the last slide. This is circular type of cylindrical, you can say this, and a circular cross section of the rib cross section. You can put the different shape of this. Okay, so this is different shape. First one you can say this is square. Then this is triangular, you can see here, and flow is here from this side. This is circular. So a different people have tried a different shapes. So this is Singh and Singh 2018. These people have tried different shapes. Okay, and there will be different types of ribs also. Okay. So in the recent development I am talking, these are the people, these are the area people work different ribs, different cross-sectional area, and duct size, duct cross-sectional area mainly I was talking, and ribs also of different shapes people have done. So this we can see here what if you put square type, what will happen? If you put triangular, circular, what will happen? So square type is rough type of structure, right? This is slightly little bit smooth than square. Here this is more smooth. So if you are putting more smooth, what will happen? Here the separation will occur early. Here it will start at this point in the square case. Here it is starting here. Slowly it is getting delayed here, this side. So smooth, if it is type of streamline flow, if you want, you should have this smooth surface. And streamline, what will we don't want this. We want turbulence, more turbulence in this. So this first one is square will give you the more turbulence and early separation of flow. And this way you will get higher Nusselt number in the first case. Higher heat transfer rate you will get, and reattachment will occur early. Here you can see this. Here you can see reattachment is going in this way. Here also it is going very far away. So what we'll find here that there is advantage, disadvantage. Here you are getting Nusselt number more, but here you will get a higher pressure drop also in the case of a square cross section. Triangular and circular, this side it will be lesser pressure drop. So we have to analyze it where you are getting how much Nusselt number is augmenting or increasing and how much pressure drop is increasing. These two ratio which will give the better ratio that we should follow. Means that it is not the direct ratio as I'm telling you. This is the THPP value, thermohydraulic performance parameter. So in that Nusselt number, we have to compare the rough surface and a smooth surface. Rough mean to say with rib, and a smooth surface, what is the ratio? And friction factor, rough and smooth, what is the ratio? And friction factor ratio, we have to make 1/3. That will give you THPP. So THPP, we have to calculate, and then you can compare. These are the things. So these are the summary of research, what the people have done, what is the can say development in recent development in solar air heater. There are various types of reefs people have tried. There are some different cross sections also. There are many experimental studies done here in this. Experimental study you will find more compared to CFD analysis. So now the people have started more on CFD also. And other one more thing is duct cross sections. People have not used different duct cross section. There are less paper in this. The reason is the flat plate and rectangular duct cross section, rectangular size is easy to build. So people have used rectangular type more. So what we will now the next part is okay. One thing is I'm not able to see. You are able to. I think Madhu, you can hear me, no? Not disconnected.
No, sir, you are audible. No problem.
Okay. Once shared this screen, then I'm not able to see that side. So this is the research gap. Now the people are working. If you are working, any participants working in this area, just I want to summarize here. People have worked on in this area. Many people worked, and different reefs configurations, different types of reefs configuration people have done. Experimental, lot of studies are available. Okay, and CFD also now people have started. Not many have done also CFD analysis. Other part is the duct cross sections. People have not tried much. Can be done, and we have done few cross sections. Okay, duct cross sections I am talking, not the rib cross section. So different duct cross sections you can take and try the different reefs. This is the one you can say future work you can do. So we will next part is we are going to start this research methodology part. People have done the numerical and computation. Oh, sorry, I wrote both same here. Numerical and experimental I wanted to write actually. So numerical part, how to do that numerical studies, little bit I'll talk on that. And then experimental part, how to do experimental study. So the thing is, if you are doing research on this, one thing I will just tell you, this area is solar water heater, solar air heater is going to become like it is almost saturated type of area. Okay, it is not very much to do in this. Slowly it is because the people have done a lot of work already done in this area. So the thing is, my research was on a different was supercritical CO2 in a solar collector. That is new, and you can find some research gap and do it. But just I'm telling you, almost many work already done. This is in that saturation site, saturated research area. Okay, so now the thing is, I'll talk about my research part. My student did it. Okay, I have one of PhD student, Dr. Nidul. He did this research under the funding of DST funded project. So in this, how to this numerical study or computational study is done using ANSYS Fluent software. Okay, you can write your own code also and do this. Okay, not the big thing. But this is a three-dimensional study, so coding will be a little bit difficult to write, will take time, but easy to do using ANSYS Fluent software. So in this I'll talk, there are two things. One, sorry, this two area of research, two section I'll talk in this. One is triangular duct, cross section of the duct is triangular, and another is rectangular with the semi-cylindrical side walls. Okay, so we have modified that rectangular cross section with a different cross section. We tried and we found that what would be the performance. This is the major thing is triangular and this rectangular with cylindrical or semi-cylindrical side walls. So these two things I'm going to talk, and with the different ribs actually. These ribs here, you can say inclined ribs, it is taken. You can see here. At the different angle, we varied the angle also, and pitch, angle, and roughness, height of that. These things we varied. So you can see here the V-type ribs we are using. The second one, triangular duct with the V ribs. Here, one more thing is, if you are doing research, you should be careful about this inlet section, how much you should take, how much exit section should be there. This is important part. Some people used to do mistake here. They will take the inlet section some random value. That won't work actually. Your paper will get rejected straight away. So you should see that what is the ASRE standard paper. You can see my paper also and other papers. Reference, you see that what should be the inlet section, what should be the exit section, and test section also how much length it should be. Because if you use the smaller size or bigger size, that the temperature, average temperature value will vary. Your result, you may not be able to validate your result with the published data. So that way you should follow the standard, ASRE standard is there, how much length you should take. In this semi-cylindrical side walls with W baffles, so different types of ribs, as I told you here, we used W type, W baffles, and we have modified these side walls. Okay, side walls, earlier it was rectangular, now we have made it smooth a little bit here. So you may try, the people can try the different cross section of the duct and different ribs combinations. Yes, you can still publish the paper. So these are the CFD model, 3D CFD models we have done here. The fourth one is semi-cylindrical side walls. The cross section is same, but discrete inclined baffles. Discrete means that you can see this. This is not continuous. So this type of things we have used. So these combinations are still, you can change the these ribs, cross sectional, different shapes. You can try and can get the performance. So meshing you can do using ANSYS software. That, and two things mainly you have to find out: friction factor, Nusselt number. These two things once find, then the ratio, that ratio will give you the thermal hydraulic performance, and that is actually that you should compare. That is the non-dimensionalized number. Even these all are non-dimensionalized only. This Nusselt number and this friction factor. You can see this. This is the what are the duct size you should take, And what are the boundary conditions you should take here? You can see absorber plate, we are putting the heat flux 1000 watt per meter square. Generally, the solar constant, you might have heard this, solar radiation, how much falling on the Earth's surface, or solar constant, when we say that is the above this atmosphere. Okay, there how much solar radiation is falling. So that is around 1400 in that range, 1361. So, and because we are doing experiment on the ground, so here it will be around 1800. It will vary. It won't be constant throughout. It will vary also. Depends on the weather condition and all. So we have taken here, we have put 1000 watt per meter square. Okay, heat flux. So this is outlet pressure, atmospheric pressure, adiabatic duct walls. Okay, these are the boundary conditions we have taken. Ductility, we have given some velocity. Okay, so different Reynolds numbers we have studied here: 4000, 8000, 12,000. You can see 16,000. And first thing is how to choose the turbulence model. So we have turbulence model. We selected different turbulence model, and which is best suitable, that we have chosen. So you can see here the Dieter's voltage correlation, you know, the very famous correlation, Dieter's voltage correlation for Nusselt number. And we can see this, it is close to RNG capsule, and here you can see this and this. So based on that, we have chosen the RNG capsule model. So you can try different conditions, different types of geometry, and you can select the turbulence model. Here you will see this, what I was telling about thermohydraulic performance parameter. You can see here, THPP. There are Reynolds number definition, you know, these are the basic part. Heat transfer coefficient, how to find this. Here also people do mistake. This Q we are supplying like 1000 watt per meter square, this Q. TP and TB you will find using experimental work, experimental study, or CFD studies. CFD study you will find this TP, TB, so with the average temperature. TB is the bulk mean temperature. So this, how you are calculating, it matters. This H will change, and based on the H, NU will change. So this thing carefully you have to select the TP, plate temperature. This also the average you have to take. TB, the bulk mean temperature of the fluid, air. Then this thing, if you take the smaller size of the test section, this will vary, and your data may not match. Okay, so these things you have to be careful. Nusselt number you calculate, then friction factor based on the pressure drop, you will be able to calculate this friction factor. Then these two, once you got, then thermohydraulic performance parameter will be like this: Nusselt number of the rough surface by Nusselt number of the smooth surface, this normal value. Without putting ribs, you get the what is the Nusselt number, and with the rib, how much Nusselt number. Then ratio will give you the how much increment in that. Then friction factor with rib and without rib. Okay, so this is divided because this is the unfavorable condition. More friction is not good. Okay, not desirable. So, and coefficient of performance, these are the other parameters you can use, like COP is here, how much heat you are able to utilize, MCP delta T divided by the pumping power. So this way coefficient of performance is defined, like thermal efficiency, how much heat you are utilizing and how much solar radiation is falling on the surface, collector surface. So that is the area of the plate into the I. I is 1000 we are taking here. So this way you can get the things. Thermal efficiency, then collector efficiency. Okay. Exergy flow, exergy inflow, exergetic efficiency. These are the things you can do the analysis. Once you do this CFD analysis, you will get the temperature. Then these things using the correlations you can calculate this side. So this is the experimental part, experimental setup of solar air heater with semi-cylindrical side walls and discrete multiple inclined baffles. So this type of backfalls we made. This is experimental study. You can see this here. This seems, this looks like, you can see the number 2 is a tester section here. From outer side, it seems like a rectangular channel, but it is not. Inside, we have put some semi-cylindrical. Okay, this channel is semi-cylindrical. So the people can do the different cross-sectional and to the study. In this area, there are less papers. I'm telling you. If you are working, you can try this also. So different, you can see here how to put thermocouple. You have to put that back side of this thermocouple. You can put 3 here, 1 here, then 3, 1 here, 3 here, like this. That you can put. And actually the in between the main and at the center, you can get the temperature profile like this, because more thermocouple is there. So more thermocouple if you put, you will get the better that average temperature value. Okay, the people used to do the outlet divided by 2. That will not give you the exact. Actually, more thermocouple you should put. So that's the reason if you go for CFD study and experimental study, there will be difference in that result. This validation, you can see this CFD with experiment. You can see here validation. There will be always this is yeah, experimental study is not ours. This is a different experimental study. We compared the same condition. We have run the simulation and compared with this. Almost it is matching. You can see here. Here the Nusselt number and friction factor. This is for the semi-cylindrical walls. This is triangular duct. First one is triangular duct. This is semi-cylindrical walls. You can see that this is almost matching. Nusselt number you are getting less, friction factor you are getting more. So then this is our study. Second one is our study, CFD as well as experimental study both. So CFD you can see, and you CFD here you are getting less Nusselt number, and in the experimental we are getting more Nusselt number here. That as I told you, the calculation problem is how much temperature sensor you have put, average how you are taking. There will be losses. Okay, so this way the thing is, main part in solar air heater, what I wanted to talk here is how to improve the efficiency of solar air heater, because it has low thermal conductivity. So the thing is, that's the reason we put RIPS to improve the efficiency, and we get almost around 60% in that range of efficiency. I'll show you that. And how to do this analysis? One is ANSYS Fluent, you can use and do that, and experimental study is also easy to do. It's not very difficult to do the experimental study in this. Here we have done the different parameters we varied, and we have calculated the performance, like Nusselt number, how much increasing. Nusselt number you can see at higher RE it will be more. Here you can see. And different rev inclination, how it is varying. You can see that 45, it is in all cases 45, we are getting the optimum, maximum Nusselt number. So similar way, you can see the 45 angle is good. You can say here 45-degree angle. This V type. Similar way, the friction factor you can see here how it is changing with the rev inclination. Okay. So 45 you can see here it is better. After that, this side you can see the more friction factor. So THPP will drop. So THPP you have to find how much Nusselt number increment, how much friction factor drop actually. If it is friction factor is less, that is better actually. So these are the different types of, you can contour, you can plot nice beautiful plots you can get in ANSYS Fluent. Okay, if you write code, this type of things getting is slightly difficult. And the 3D coding you have to do with the with the turbulent model you have to implement. So you can see here thermohydraulic performance parameter for 45-degree angle. You can see in the top one, it is around 2. So we are getting around 2.01 in this case of triangular duct. What people have done with the rectangular duct, these things 1.44, 1.98, but not much improvement. You can say it is almost 2.01 only with this. Okay, so this is for the triangular duct thermohydraulic performance. So final comparison you should make using thermohydraulic performance parameter. This will give you the exact comparison, you can say. Otherwise, Nusselt number may vary, but friction factor may also increase. So you cannot decide there which one is better. The best thing you have to use is this parameter, thermohydraulic performance. This is the exergetic efficiency. Exergetic efficiency in all cases, and we calculate. In this, actually, this is very low. The reason is in this we consider the sun temperature, like Carnot efficiency of any heat engine. If you find, so like 1 minus T1 by T2 or T2 by T1, whatever you say, in that. So that the temperature, the source temperature and sink temperature. Source temperature we consider here sun temperature. Sun temperature is very high. So that way, how much you will be able to utilize, then you will get exergetic efficiency. So it will give very high first law efficiency, Carnot efficiency, because sun temperature you are using very high temperature, but utilization is very low here. It's very low how much you can use, because here reaching at around how much the thermal efficiency, when you will find here your plate temperature will be 60, 70 or 100 degrees Celsius in that range. So this much you are utilizing and getting the efficiency, the heat engine efficiency with sun temperature. If you use, then it will be very huge. The ratio will be very less. So that's the reason here we are getting 2% in that range, 2%, 3% exergetic efficiency. That depends on the which formula you are using for the exergetic efficiency. So most of the people have used the same. So to comparison purpose, we should use the same formula. This is the summary of this part we were doing for this part for the triangular section part. Okay. As I told, 1.32, 2.01 we are getting thermohydraulic performance. In that, again, the different reef we have taken here. This is with inclined reefs. So first one was without reefs. Here we are putting the inclined reefs, I think. Yeah. So here we have put different reefs, and we have got this type of graphs will get, sorry, we'll see that. With the THPP between ribbed triangular duct and rectangular duct. So same rib we have put in the rectangular duct and triangular duct. Then we compared it. We are getting, you can see this rectangular channel if you are using, duct you are using. Then you are getting around 1.6, 1.5 around this red one you can see. And black you can see around 1.7 here, 7.5 you are getting. This much difference is there if you are using triangular in place of rectangular duct. So there will be advantage in this. Getting around, you can see here 60.4% and 55% reduction. This is the moisture ratio. Is actually we tried, like we have done experiment using this solar air heater for drying the food products, banana and all. So this is the summary of the second part. We'll go to this one, semi-cylindrical side walls and WFL. So this one we have done CFD as well as experimental work also. So if you do these two type of things, you can compare. This is the rectangular one. This is the semi-cylindrical side walls. You can see this is the smoothened actually. This part you can see the corner part. So corner part extra, you can see that vortices were there. That is gone. It's not there. So this is giving slightly better result. This is the validation part. Nusselt number and friction factor with the vertical side walls and cylindrical, semi-cylindrical side walls. You can compare here. You can see the Nusselt number, how it is. Nusselt number is, there is no change, almost same. But friction factor, there is a change. Vertical side walls, you can see the higher friction factor, but this has semi-cylindrical lower friction factor. So this way, Nusselt number is not changing, but friction factor, your pump power will reduce in the case of semi-cylindrical. So this way you will get higher THP, the ratio. And another thing is, if you put the inclined way, like this type of inclined ribs, if you put, there will be secondary flow, as I explained earlier in the introduction side. So that secondary flow creates additional turbulence, you can say here. This side, you can see this secondary flow. This side, how it is coming, you can see the secondary flow part. So that enhances the heat transfer rate or Nusselt number, you can say finally. So you can see here the semi-cylindrical side walls, if you use, you are getting around 2.27. You can see the changes. These are all rectangular, different baffles. You can say W baffle they have used here. 1.8, 1.9 they have got, 1.98 around 2, you can say. Here we are getting 2.27. This much changing. So thermal efficiency, let us see here. This is the thermohydraulic performance with the different pitch and ribs height. Then thermal efficiency, if you compare, this is around, you can see it is going around 72%, around 71 or 72% in that range. It is going present studies. So the efficiency, as I was talking earlier also, the efficiency you have to increase, and this efficiency 70% is, if you compare with the photovoltaic cell, that is 15%. It's quite high, not quite high, very high, 5 times higher. So this way, for the drying product, this has a scope. This is a better choice. So these are the things what already I talked. .27 we are getting here, THP. And you can see here also exergetic efficiency part is around 0.02. Means this is not a percentage will be 2% around. You can see here enhancement. In the energy efficiency and exergy efficiency, both we have just I showed you here the exergy thermal efficiency is called energy efficiency. You can see this, the enhancement with this much you are getting. And this is solar air heater with semi-cylindrical side walls and multiple discrete inclined baffles. There are the multiple, but this is discrete, not the continuous. We used till now the continuous. This is the discrete. So discrete baffles, if you use that, this will give you around thermohydraulic performance. You can go around. It is 2.8, around 2.7. You can say in this range. If you 2.69, yeah, it is written here. 2.69. Here 3.07. 3.07 is not shown. This is, oh, that is the heat transfer enhancement. 2.47 times is obtained for multiple increments with the gap at for this times increment in friction factor. Okay, this 3.07 is the increment in friction factor. We don't want this increment in friction factor. We want increment in Nusselt number. So total Nusselt number increment here you can say 2.47, and in this 3.07, the ratio you can see 2.69, because here we have 1/3 in the friction factor, which is not the direct ratio. So this is the semi-cylindrical side walls, and you you can say square cross-sectional reef with the discrete reef, you can say W type discrete reef. Can get, you can see here the present study here 2.69 we are getting. In this collector efficiency, it is going around 68% something in this range here, 69%. Coefficient of performance is around 4 times the pumping power you are getting. You can say how much heat you are getting, how much pumping power you are using. That ratio is coefficient of performance. These are the summary. Almost same thing is here. Say up to 70% we are going to higher collector efficiency. And the other conclusions, details, what I already talked in that. So we are getting, yeah, almost I already explained this 3D safety steady state simulation we have done. 17% higher THPP case in this triangular, and there will be semi-cylindrical 38.7% in exergetic efficiency we are getting. This is the okay. So most of the things I explained. If you have doubt, you can ask, and we'll go to the final scope of the future work. What are the things earlier? Also, I was talking about this. What you can do, different types of cross section you can choose and do the different reef combinations. That is one thing. And there's sharp corners of the duct can be smoothened, and that you can focus study on that, how to increase the heat transfer in the corner area. Flexible ribs. One idea is flexible ribs or turbulators can be employed. Okay, so this will be a good idea, flexible ribs and turbulators, to reduce the additional pressure drop that mitigate the potential gain in heat transfer rate. Phase change materials also you can use. In this, actually, if you use phase change material, your collector temperature will be almost constant, you can say. If you put the phase change material in the collector plate itself, then it will be almost constant. It will melt it, and it will not rise. Sometimes temperatures, if you are not able to extract heat, then temperature will rise and losses will be increased. So see, the higher temperature is not good in the solar collectors. Higher temperature, it will create more losses. Always. So that one thing, if you use phase change material, that also will be good. Another thing just I wanted to do here is, if you are working on AI and ML, artificial intelligence, machine learning, that also you can write code, because there are a lot of data available. Those data you can use and generate some correlation. Train the use some data, and you write code and get some correlation. That way also you can publish few papers in this. These are the reference. Okay, just acknowledgement, because this study was carried out by my student Dr. Nidul under the supervision of myself and Professor Anis at NIT Surat, under the research grant funded by DST, Department of Science and Technology, New Delhi. So thank you very much. And now, please, if you have any questions, please ask. Yeah, Madhu.
Hello, sir. Yes. Participants, if you have any questions, please, we can ask to the sir.
Hello, sir.
Yes.
Myself, Dr. Manish.
Yeah.
Sir, you have shown in the beginning regarding the solar powered various application. So is there any mechanical mechanization of that powered we can change their direction with respect to date, time, and season.
Again, can you what the mechanism you want to ask? What?
Yeah, is there any mechanism have you seen now regarding that that can change? Not electronic. I'm talking about electronic or sensor based. I am talking based on mechanical element. It can change based on the date, night, and season, based on season, because the direction of sun changes with the day, night, and according to season also.
That is called tracking system. Okay, solar tracking system you are talking about.
Yeah.
So solar tracking system. The thing is, one thing is you have to use data you can put in that. You will get the, because the different day data you will get from the website also. At what days and what would be the inclination, those things you can put in that, and automatically that you write one code in that, and that will run the servo motor to shift that. You can do that two-way tracking and single-way tracking also. So based on that two motors, if you use, it will always point your the solar collector part towards the sun. So the thing is, this type of work also people have done. Tracking system you will directly, you can buy also, tracking system is available. So
No,
one thing is,
I want like not like based on sensor. I want to just like mechanically kind of thing with like based on the gear mechanism, all those kind of thing.
yeah, gear mechanism, but someone should rotate it, na?
Yeah.
So someone should rotate, so
The
that
motor.
you need servo motor, motor to rotate it.
Yeah.
And servo motor, how it will work, you have to give that command to that. For that, what I am telling, if you don't use sensors, which I didn't talk about the sensor, I talked about you can feed the data directly, and based on the data, if which day it is, based on the data that servo motor will rotate that much, okay, and time and all things you are giving in that, so accordingly it will rotate. Gear and all mechanism, if you want manually to rotate, then that is different. You know that you can do it.
Not manually. My point is not based on electronics and sensor.
Electronics I removed, sensor removed, only the motor you need, na?
Yeah.
That part is required. Okay.
Thank you, sir.
Welcome, Ajay.
Good evening, sir.
Yes, good evening.
Sir, good evening, Yadav, sir. Hope you
Aslam
remember
ji bol
me.
rahe hain? How are you?
I am fine, sir. How are you, sir?
Yeah, good.
Thank you, sir. Just now only I came to know, I mean, a few days back only I came to know you joined IIT Patna.
Oh, you are not knowing, huh? Okay.
No, I'm not knowing, sir. I thought you are still in NITK.
Yeah.
I do have some couple of questions on this topic. Question is, sir, in one of this slide, in a graph, you have shown like high average temperature versus collector efficiency. So in that, what we can conclude is as the high average temperature increases, collector efficiency is decreasing, it's becoming low. To show you, throw some light on that, sir, for what reason it was happening so.
This one, na?
Yeah, sir. Right, sir. Same.
So what you wanted to ask in this?
Like what was the reason with the increase in average temperature, the efficiency is going.
Okay. See, the main disadvantage of solar collector part is we cannot insulate the top part, right now, because the solar radiation should come inside.
Yes, sir.
So we cannot insulate. We can insulate the bottom. We can reach up to the minimum or almost zero heat transfer rate from the bottom side or side walls, we can make the good insulation in that. But the top part we cannot remove. No? Top part we don't have option how to insulate it. That glass has to be there and the radiation has to come in that. So what happens as your temperature increases, that air temperature or water temperature in the solar collector, at higher temperature if you are operating, what will happen with that higher temperature, there will be losses towards that glass side. Okay, that is the open, you can say the glass, through the glass there will be losses. Glass has some conductivity. Conduction loss will be there. That you cannot remove. There will be vacuum also in that. Vacuum part people creates vacuum also. In that also there will be some losses. Complete vacuum you cannot create. Okay, and there will be some infrared losses. Infrared can cross that. This glass. So these are the issues actually. That is the big problem of this. You cannot do that, insulate the top part. So top loss always will be there. So to reduce that, there are double glass, there are different vacuum level we create. Okay. So in that we can little bit improve efficiency.
Okay, sir. Yeah, I got it, sir.
Okay.
Yeah, second question was related to the relative rib height and pitch. Can you tell me which is the value to use height and pitch, relative part, relative rib height and relative pitch out of the
actually like rib height, no? This thing I've given here some 0.03 to 0.05. This thing you have to do the study, different cross sections if you have, different types of ribs if you have, it will vary. Okay, so I've given just approx some data. So it may fall in between. Okay, and for some cases it may exceed also a little bit, not much. So this range I have provided here. So that depends on you. If you do the study here, CFD simulation you do, you will get the optimum value. Based on that, you can make the experimental setup.
Okay, sir. Okay.
These data I have given here. That's the reason. 0.03 here in this case, and this case 9 to 15. This is how much gap is. It will vary for different Reynolds number. Right. There are many things. There are hydraulic diameters. It will vary with the hydraulic diameter also.
Right, sir.
Okay.
Yes, sir. Thank you, sir. And even one of my, one of a student who is working under me for this PhD, he's working on the same thing, but then he's investigating the effect of some aerofoils. Macro aerofoils.
That type of things also you can use here.
Yeah, yes, for the enhancement of the heat transfer characteristics, particularly in the tube flow. So will we go for the same Dittus-Boelter correlation if it is going to fit in a turbulent region?
That you can go. The thing is, one thing what I will suggest, this aerofoil type of shape will have less pressure drop, but how much it will enhance the Nusselt number, that you have to check. Enhance less Nusselt number also in that, improvement in Nusselt number. So if it is fluctuating type, suppose it is moving, okay?
No, sir.
Moving means that is...
no, right now we are not thinking of moving part. We are going to
stationary.
fix it. Yes, sir, stationary only.
If you put some spring and do that, in that, okay, connect with the spring, it will automatically move up and down. So that type of things you can try.
Fine, sir.
Experiment you can try the different, but getting the results in CFD will be difficult. In that.
Okay, sir.
Okay.
Let us see the feasibility. Thank you, sir. It was very nice to talk to you.
Good evening,
very
sir.
nice to talk to you after a long gap.
Good evening, sir. I am audible to you.
Yes, yes, yes. Please.
Yeah. Myself, Sridhar Kedar from Cummins College of Engineering, Pune.
Acha.
Sir, regarding my question for solar air heater systems, in a widely many of the researcher in case of the Indian around the countries, they have to be used for evacuative collector as well as flat plate collector and compound parabolic concentrator also in case of the solar air heaters. And now the latest current trends in case of the solar air heaters, they have to be mainly used for the phase change materials. And one of the famous phase change material, that is a paraffin wax. So my question regarding this phase change material, what are the different materials for these phase change materials are available in case of the solar air heater for improving the energy performance assessments, so that they have given the better rate of performance actually.
You see, the thing is, you will get lot of phase change materials if you search it.
Yeah.
Okay, so based on your requirement of temperature,
yes,
you
sir.
need, suppose what is the application, based on that you will fix the temperature. And
Yes.
always you try to operate at the minimum required temperature. No, don't go to the higher side. Higher side, if you go, then there will be losses. Loss will be more. So as I also talked, this phase change material people are using, but the other problem of the phase change material, the name, as if you ask, there are paraffin wax is there, that probably it will go to 60 degrees Celsius, RT 58, RT 60. There are different equation. Then salt based is there. There are higher temperature. At higher temperature, if you go, okay, it's 200 degrees Celsius also you can go in that. So as you go higher and higher temperature, your efficiency will drop. This is the one thing. So if you want to dry something, some agriculture product, some food product, you want to drying temperature, suppose 90 degrees sufficient. So the thing is, you operate in that range, 190 in that range. Don't go to the 150. We will get the higher temperature and we will dry it. Then your efficiency will drop.
Because if you can increase the temperature, then there is a temperature loss and efficiency goes down.
Yes.
Therefore, manage the temperature within the 60 degrees Celsius to 80 degrees Celsius, so that we can improve the energy efficiency. Likewise.
Correct. Okay. So these are the things, different phase change materials you can use. One major drawback of the phase change material is the low thermal conductivity. So conductivity of the phase change material is very low. So you have to mix some nanoparticle or something. You have to make that thin layer of that. Okay, phase change material in the thin layer, so that that conductivity will not be there.
Not up to the mark actually. Yeah. Okay, sir. And my second question. My second question regarding this, regarding the mathematical modeling point of view. So, which are the different parameters? Say that the flow parameters, laminar, transient turbulence, or different dimensions parameter you can take into considerations for the solar aerated systems. As per the mathematical modeling point of view, which parameter you can take into considerations, so that we can prepare the better equations, so that we can go for the experimentation and then put the value and we get the better results as per this modeling point of view.
See, the thing, one thing is Reynolds number matters a lot. Okay.
Okay.
So,
yes, sir.
Reynolds number, if you increase, one thing is Reynolds number, higher Reynolds number, you will get better Nusselt number, but power also will increase. Okay.
Yeah.
So this is one thing. Another thing, if you are putting the reefs in that, and optimize it, final, as I talked earlier, the thing is final part is THPP, thermohydraulic performance parameter. Whatever you vary, you see that whether THPP is increasing or not. Some case you will see that Nusselt number is increasing very large, very high, but you will find that friction factor is also increasing. So the thing is that THPP, what equation I showed you, This is the very common equation. So you have to final check is this point at HPT, how much it is increasing.
Okay, sir.
Okay.
Thank you very much.
Sir. Thank you, sir.
Thank you, Sudeep.
Thank you very much, sir. In spite of busy schedule, sir accepted our request, and he gave the very nice session for 2 hours, so which will be really helpful for all the participants. Even as sir told, like food industry nowadays, we are more focusing on the food industry, the whole era. So there we can utilize the air heaters in a proper way. And even sir has nicely discussed regarding the different types of ribs and how they are helping to increase the efficiency. So this will be, sir, very initiative and very informative session, sir. It was. Thank you very much, sir.
Thank
So
you,
once
Madhu,
again,
for the invitation.
I would like to thank from Nutan Maharashtra Institute of Engineering and Technology on behalf of Mechanical Engineering Department. So once again, thank you very much, sir.
Thank you, Madhu. I think Tavis is also there.
Yes, sir.
Yes, sir. Yes, sir. I'm here, sir.
Oh, great. Good.
Yes. We have the Dr. Tabish Waidi's session also, sir.
Okay, good.
In coming sessions, I mean, next on 4th day, we have the session from Dr. Tabish also, sir.
Okay.
And now this is
good,
sir.
We are there.
We are moving to the next session, sir.
Okay.
Now we have the another session at actually it is planned for the 8 p.m. 8 p.m. to 9:30.
Yeah, I exceeded, I think. Okay, so thank you.
No, sir. Thank you very much, sir.
Thank you.
Dear participants,
come out. Stop, Karu.
Yes, sir.
Sir,
Yes.
will you share the slides, sir? It's a humble request.
Yes, definitely we'll
Share with the
the
other
slides.
Okay.
We'll share the slides with you, people.
ठीक. Thank you. मैं out हो रहा हूँ. ठीक.
Yes, sir. Thank you.
Thank you, sir. Thank you.
Now it's time to move for the second session. The second session speaker, he already joined the meet. So just a minute, sir. Now I request Dr. Satish More, sir, please introduce brief introduction, give the brief introduction regarding the next session speaker, sir.
Thank you, sir. We are having the second session from 8 p.m. to 9:30. We are having the speaker for this session from USA, Dr. Sudeep Ingole. Regarding the introduction, Dr. Sudeep Ingole completed his undergraduate in metallurgy from the National Institute of Technology, Nagpur, a Master of Engineering in Manufacturing Engineering from Indian Institute of Science, IISc, Bangalore. He holds a PhD from the University of Alaska in Mechanical Engineering, interdisciplinary. He worked in industry and taught engineering subjects or courses at Texas University. He is self-employed and residents in Houston, Texas. He worked in engineering contract research, innovation, technology development, especially in materials and mechanical engineering. He has several international patents published in US of America, Canada, Europe. He regularly serves as a journal paper reviewer and also published the number of international and national journals. So I welcome Dr. Sudeep Ingole. for the today's session. Sir, please share your screen. So we will start that session.
Oh, hello all. Can you hear me?
Yes, sir. Yes, sir. You're audible.
Okay. Let me share the screen.
Yes, sir.
Dear participants, we have the automatic attendance monitoring system. So you should have at least 80% of the attendance for each session. So I kindly request all the participants to attend the sessions, and you can get the certificates at the end of the session from the attorney.
Could you see my screen?
No, sir.
Just give me 1 second. Okay? I'm
Yes,
trying to. Can you see it now?
No, sir. No. Yes, sir. Now it's going. Yes, sir. Now it's visible.
You won't be able to see if the screen. So I have the presentation mode.
Yes, sir. Now the screen is visible. No problem.
Visible, right?
Yes, yes.
Wonderful. Good evening, all. Thank you, Dr. More, for a nice introduction. I never thought about this detailed introduction. Thank you very much. Today, we are going to discuss a little more very basic about the tribology. This includes some of the fundamental principles and measurement techniques used to study the tribological parameters of engineering material. Hello all and welcome to this training session. My name is Dr. Ingole. I'm based in Houston, Texas, and I have worked in surface engineering and tribology for most of my career, may it be in academia or in industry. Currently, I'm working as an independent service provider based in Houston, primarily focusing on the clients in oil and gas industry. I thank the organizer for providing me this opportunity. As there will be some complications if we keep the session active interaction during the presentation for question and answer, what we will do is we will keep all the question and answer at the end of the presentation. Will that be okay with all?
Yes, sir.
All right. Thank you so much. Let's focus on some of the very, very basic role of friction and wear, and then we'll go to some of the fundamental parameters. As you know, friction plays a very important role in our day-to-day life. Similarly, it also plays a significant role in several engineering systems that leads to optimization of their performances. Some of the applications in engineering industries, such as transportation, manufacturing industry, biomedicine, bioengineering industry, textile industry, these are just a few names to give out. There are several other industries where tribology plays a very significant role. If we discuss a specific application in these industries, for example, transportation and manufacturing industry, we will have friction rings, cylinder linings, bearings, gears, cutting tools, inserts, rotors, etc. As most of the participants are mechanical engineer, this might be a very short list for them, and they can relate a lot more other applications where friction and wear plays a very important role. There are numerous mechanical systems that have friction as an integral part of their performance. In the biomedical and bioengineering industry, some of the applications where friction plays a very, very important role are medicinal pills that everyone is aware of. Endoscopy instruments. Some of you may be aware of surgical robots. Implants, for example, artificial joints. This is not the complete list where friction plays a very important role. In textile industry, some of the components, for example, yarn feeders, draw rolls, thread guides, where friction plays a very important role. Think about an immature failure of these components, which can disrupt the entire production process. And then it will relate it to the energy loss, monetary loss, time, production loss, as you can relate those parameters. Performance, reliability, and service life of mechanical systems depends on friction characteristics. In other words, friction plays a very important role in determining the efficiency of the mechanical systems. Take a simple example of a human hip and knee joint as a mechanical system. Due to the age-related or untimely damage to the systems, the friction characteristic at the interface changes, and the overall life of this joint drastically reduces. These joints are often replaced with artificial joints. Again, artificial joints have their own life. They do not last forever. Therefore, again, we need to think in terms of their longevity from the surface preparation point of view. Some of the facts that, well, before that, let's discuss some of the facts about the friction and wear losses that can occur to the mechanical systems. Resources wasted at the interfaces can add up to more than $40 billion per year. That is alone in the US. Now you think about rest of the all. You think about overall the area where these losses can be occurred. Some of these losses can occur at the interfaces such as friction ring cylinder, interface tools, workpiece interfaces, drills, and hole interfaces. Do you know that tribological improvement in automobile sector alone, if we have better performances of these systems, we can save around 18.6% of the total annual energy consumption by the automobiles. The saving will be in several tens of billions of US dollars. Now, that is motivational enough to be involved in tribological inquiries to make the contribution to the country's energy saving, isn't it? Now, if we add one of the another component to this friction and wear losses, that is corrosion, and you can see the cost of corrosion that impacts on the US economy. I took these numbers a little older actually, but then you can relate. If you calculate those into the current situation, the cost of corrosion in 1999 was $8.79 trillion US dollars. In 2016, actually, the US GDP was around 13.13 trillion US dollars. And current GDP around 21.43 trillion dollars. Well, if you consider the direct cost of corrosion is around 3.1% of the US dollars. Let me give you a very simple schematic of how these energy losses occur and where exactly what industries or application fields these are. Now, if you look at this status, this is very interesting. This is the cost of corrosion in different application sectors, and you can easily see that the application area such as motor vehicles, water supply systems, and very interestingly, the defense sector has a huge cost due to the corrosion. In several of these applications, surface chemistry and some of the tribological properties plays a significant role. When the loss due to corrosion is combined with the tribological losses, it is staggering. With this, in the few next slides, we will return to our understanding of some of the very fundamental parameters that we can implement in our inquiries that can reveal very, very important information and its application to the real life areas. So one of those measurement parameters is the surface finish. Surface measurement is governed by the ASME standard B46.0, and this parameter usually measure the surface roughness, waviness, lay, and unrelated damages. Visibly smooth surfaces might have more features on them when looked closer at or at very high resolution. Theoretically speaking, when we look at them at the atomic level, all surfaces are rough. The material at all level of length scales have some features on them which make them irregular. The smoothest surface, we can call it atomically flat. As you may know that the surface, the material we call at mica, when mica is cleaved, it produces two atomically flat surfaces. Even then, the smoothness is not long range. We will see several atomically flat sections, but then there will be unevenness. But for most engineering applications, the atomically flat surfaces are not required. These flat surfaces might improve the performance of engineering surfaces where they are used. It will be costly actually even produces this type of smooth surfaces. But then there is always a trade-off. It is very essential to express these surfaces in a qualitative and quantitative way to identify their influences on the surface properties and their performances. Several techniques are developed over a long period of time to measure these irregularities. We will discuss them eventually in this training module. The unevenness of the surface, when measured quantitatively, it turns as surface roughness. When we consider the reference plane on the surface, there will be valleys and peaks in three-dimensional space. With reference to these planes, when we look at the two-dimensional section, it will appear something like this particular image. There is another term used to describe these surface features is called surface texture. Typically, surface texture also includes the surface properties that are not contributes to the surface roughness. These properties are surface waviness, as I mentioned, unrelated damage on the surface, what we call it as the flaws, and the lays. According to the ASME standard B46, lay as the predominant direction of the surface pattern. Lay is ordinarily determined by the production method used. Roughness is the finer spaced irregularities on the surface texture. These irregularities usually results from the inherent action of the production process or the material conditions. And the waviness is the more widely spaced component of the surface texture. Waviness may be caused by various factors, such as machine, workspace deflection, vibration, or chatters. Let's talk about some of the individual surface parameters. There are several parameters can be calculated from the surface profile. These parameters will be discussed in the following sections in little detail. Some of the parameters are of prime importance, which includes every surface roughness, root mean square of the surface roughness, maximum profile peak height, maximum profile valley depth, maximum height of the profile, average maximum profile peak height, average maximum height of the profile, maximum roughness depth, mean spacing of the profile, irregularities, and the peak densities. We will discuss some of these parameters. For example, the arithmetic average. We'll talk about some of the parameters are R sub A, R sub Q, and the list of the list is given, but we will talk about that in calculation of individual parameters. The R sub A is arithmetic average deviation of the accessed profile, whereas R sub Q is root mean square deviation of the accessed profile. And we will talk about that individually, eventually. In order to calculate these parameters, the most important thing is that the measurement itself, the profile sampling itself. So in order to calculate these profiles, we have a couple of different length parameters that we need to consider. One is the transversing length. This is the length determined to select the evaluation length. Transversing length is always larger than the evaluation length to eliminate the end effects of the measurement tool. Second one is the actual evaluation length, the length used for roughness and waviness measurement. And third one is the sampling length, the profile length to evaluate the widest irregularities. Sampling length is always smaller than the evaluation length, and which is given in this particular cartoon actually about all the different lengths. Let's go to the next about surface measurement, surface parameters. We will discuss how to calculate some of the parameters from the surface profile taken. Let's talk about how to calculate the average surface roughness. Calculation of average surface roughness, which is denoted by R sub A. Average surface roughness is designed by capital R and with subletter A, where, right. So, well, in terms of mechanical engineering, I think this is one of the topics that is being learned in some of the courses that I assume, if the syllabus is not changed. The average surface roughness is denoted as R sub A. This notation is commonly used in the United States, and it is also defined by the ASME standard. Surface roughness or the average surface roughness is defined as arithmetic mean deviation, the surface peak, and the valley from the mean line. And it can be given with this simple formula. The applications of average surface roughness, as you consider, are why average surface roughness we need to calculate. Surface roughness is most commonly used. First thing is it's very widely used parameters in order to calculate or relate the surface performances. Second, surface roughness measurement has a very good statistical stability. And most commonly, this is the default called out on the drawing unless it is specified. So surface roughness is also included into the design parameters. But there are some disadvantages of surface roughness. Average surface roughness treats peaks and the valley the same way. It is not very useful for specific purpose surface is such as seals and etc. Let's move to the next parameter. Let's discuss about how to calculate RMS roughness, which is denoted by R sub letter Q. RMS roughness is defined as root mean square deviation of surface profile from the mean. RMS roughness can be calculated using this formula. I'll not go into the details of the formula. I can hand over the slides so you can refer to the formulas. I would like to just give the overview so that we can focus onto the wear and energy losses section of the presentation. In this formula, the length is L, which is given is the evaluation length. That is very important to consider. And Z is the measured height at every position along the profile length of the axis. For digital profile, RMS surface roughness can be calculated using this equation. What are the applications where the RMS surface roughness being used? It is very similar to surface roughness and can be replaced with each other for general purpose use. For Gaussian distribution of the surface height, RMS roughness is equal to 1.25 times the surface roughness value. So RMS roughness used to control surface, which is used in particularly scientific purposes. The next parameter is maximum profile peak height, that is R sub P. It is calculated as the highest peak of the profile from the mean line along the evaluation length. The next parameter, these are little less significant parameters. Most of the most important parameter that is being used is R sub A. So average maximum profile peak height, this parameter is calculated as the average of the successive values of R sub P and measured over the evaluation length. Next parameter is maximum profile value, that is R sub V. It is the depth of lowest depth point of the profile from the mean line over the evaluation length. Whereas maximum height of the profile R sub T, it is the distance between the highest peak and the lowest valid depth point of the profile within the evaluation length. The next parameter that can be considered as R sub Z, the average maximum height of the profile. It is calculated from R sub T measurement. It is the average of successive value of R sub T calculated over the evaluation length. And the maximum roughness depth, that is R sub max, it is observed from the R sub T measurement. It is the largest of the successive value of R sub T calculated over the evaluation length. The amplitude density function, we can also refer it as ADF, is the probability density of the surface height. The amplitude density function is normally calculated as the histogram of the digitized points on the surface profile over the evaluation length. And there is one more important parameter actually, that is the profile bearing length. The This is defined as the summation of the section length obtained by truncating all the profile peaks with a parallel line to the mean line within the evaluation length. The height of that line from the mean line is specified by P. How does the height of P from, or we can also refer it as sometimes as a rho, from the mean of the line specific as the length from the highest peak with an optional offset, and as a height from the mean line as the percentage of R sub T value relative to the highest peak. And another parameter that is what we call it as a bearing length ratio. It is the ratio of the profile bearing length to the evaluation length at the specific level of roof. The next parameter is bearing area curve. It is also called as Abbott-Firestone curve. It is related to cumulative distribution of ADF that we already saw. It shows how the profile bearing length ratio varies with the length. Some of the advantage of BAC are the bearing area curve is useful to predict the run-in during the wear, or sliding of the surface is, for example, cylinder liner, rolling, or bearing surfaces. Surfaces like coatings, electrical contacts, and seal, etc. As for the ASTM standard Y14.36M, there are some of the symbols that are being used on the drawing those are related to the surface measurement, where A roughness value R sub A is one single parameter, and sampling length or cutoff is denoted by A. If you can see the symbol is shown here. B is the production method, treatment, coating, and it also gives the note for call out, or some other parameters also can be included here. C is the surface cut off or sampling length. D is designated as direction of lay, and E is minimum material removal requirement, and F is roughness value other than R sub A preceded by its parameter symbol. If you take the example of R sub Z, or you can also mention the value of any other parameter other than R sub A. And material removal symbol is, as you know, that the triangle shown as a material removal symbol for that, directing to the surface. Now, in order to get all this data, there are different methods developed, and these all methods are particularly designated or characterized into mechanical, optical, scanning probe method, some fluid methods, and electrical methods, and electron microscopy method. We will not go into all details of each of the methods. However, we will see little detail about the mechanical method. A typical measurement, consists of the stylus measurement head with a stylus tip and a scanning mechanism. The measurement heads, the tool actually has the stylus arm and sensor assembly with the loading system. The stylus arm is coupled with the core of LVDT or motor vehicle motions. A core of the force solenoid is coupled to the stylus arm, and its coil is energized to load the stylus tip against the surface. A proximity of the probe is used to provide a soft limit to the vertical location of the stylus with respect to the sample. The sample is scanned under the silos with a constant speed. Now this is a very simple tool that is being used in industry for very long time. With advanced technology, there are other tools being developed, but most of the other tools are mostly utilized at the laboratory level or research level or for the inquiry purposes. But the industrial tool that is being used is the mechanical tool, and nowadays we also use some of the optical tools to get these surface parameters. Now, where these particular parameters or surface roughness is being used, there are many different industries where this surface roughness, simple tool measuring the surface roughness plays a very significant role. And some of the industries which are benefited actually in order to save the dollar amount, the energy losses because of this simple tool. So some of these industries are dairy and dairy food and beverage industry, medicine and biomedical industry, oil and transportation industry. What exactly the application of surface roughness measurement in dairy food and beverage application industry? Can you think about where exactly the surface roughness plays a role? Very simple tool, but its application is very at a very huge scale actually. The average household purchase of a dairy product. Think about in Indian household family, how many products do we use? Those are derived from the dairy. In the US actually it is even at a higher level. It generates a multi-billion-dollar industry, the dairy industry. Where do you think about the surface roughness parameter comes in picture? If you think about the containers and the handling equipments where all these dairy products are being processed, is the sanitation of these equipments. So in order to keep the this surfaces clean, or the ability of the surfaces to make sanitized, is a very simple parameter, is the surface roughness of those equipments. If you think that if these surface parameters can be controlled, and as a matter of fact, in these industries, the surface parameters of the surface roughness or surface smoothness of this equipment is governed by the standards, and that will contribute to these energy saving or even for the health-related issues. Think about the medicine and biomedical industry. Surface, as we discuss about one of the application actually in biomedical industry, is the implant applications. As the surface texture is improved, the fully hydrodynamic lubrication is obtained at the lower and lower bearing velocities, particularly at the hip and hinge joint applications. And actually the wear is reduced, resulting in the longevity of the implant material. Or automobile manufacturers also have utilized surface measurement or these techniques, particularly application focusing on the oil consumptions, even in electrical motors. Think about the paint and surface modification industries, where the surface roughness measurement or surface parameters plays a very important role. Again, in electronic industry, when we talk about the applications of surfaces, again, it's very similar to the dairy and food beverage industry, where the cleanliness of the surfaces, the foreign particle inclusion in electronic industry is very detrimental. It can stop the entire manufacturing process. Well, I will let you think of other numerous applications where this a very simple measurement technique plays a very important role in your inquiries. And you can also think about how you can incorporate it into your inquiry, into your research. Now, these simple techniques can be incorporated in your master's thesis project, but its application could be very, very vast. We can see that many of the institutions, they do not have the infrastructures, that can lead, sometimes frustration that the master students or the postgraduate students, what we call, face the difficulties. But particularly, these simple techniques can be utilized into the inquiries. Let me turn the focus towards the friction and its results on the surface damage from the rest of the presentation, and then we will move to the question and answers. Well, let me discuss a very simple, that the tribology has contributed to human culture over hundreds of years. It is not studied for centuries. It is studied for centuries. I think the first person who studied the friction and friction, it was Sir Leonardo da Vinci, and he was the first one to study the friction in a very scientific method, where various sources have described tribology as the science of mechanism of friction, lubrication, and wear of the interacting surfaces that are in relative motion. It is also considered as a branch of mechanical engineering that deals with design, friction, wear, lubrication of interacting surfaces as bodily joint or in relative motions. It is also branch of engineering that deals with the interaction of surfaces in relative motion, their design and friction, and wear and lubrication. But whereas, in general application or its uses are concerned, tribology is a very, very interdisciplinary field. It is not just the part of mechanical engineering. When it comes to the studying the surfaces, development of the surfaces, many of the other science majors can be coming together and form an interdisciplinary team. Friction is a fundamental surface response of a material. The concept of friction was used in ancient time, and this particular cartoon is a very simple method. At that time, it was a scientific method to measure the friction. And this particular cartoon was taken from one of the books on Leonardo da Vinci. The concept of friction, as I mentioned, that this is very ancient methods to incorporate friction into the study. There are many evidences found which strongly support the use of this particular concept. A scientific study of friction was first reported by Leonardo da Vinci, who was, as most of us know, was a painter. He was born in Italy and worked as a painter. Then he also worked as engineer, and then he also worked as an architecture. You will not believe, you maybe know, actually, some of you may know that it was Leonardo da Vinci who actually started studying the anatomy of the body. Actually, he started drawing the different organs as he was also a painter or artist. This is just a fun fact on the side. It has nothing to do with the friction and wear. He studied very important aspect of tribology. For example, he studied friction, wear. He also studied bearing materials. He also studied lubrication systems. He also studied gears and screw jacks. He also studied the rolling bearing, element bearing as well. So, in simple words, Leonardo da Vinci's contribution to surface science, you can say it's very foundational and significant. In 1969, Amanton law of friction were introduced. These laws were actually explained by Leonardo da Vinci itself, but his transcripts were all hidden actually, and they were, or they might have lost. Amanton and Charles Colum actually gave a valuable contribution to the tribology study. Their findings were, still applicable in engineering problems today. Some of them are listed here, which are applicable to dry friction only. One is the force of friction is directly proportional to the applied load. That most of us, use this particular law even today in our engineering application. The force of friction is independent of the apparent contact area. That is AVANT on second law, what we call. And the kinetic friction is independent of the sliding velocity. Though there was wide impact of lubrication in everyday life at that time, but it took some time to incorporate the effect of lubrication in the studies. Bowden and Tabor developed a theory called theory of adhesion. The adhesion concept of dry friction was first proposed by another person. His name is Desangulier, and was applied with great success by this pair, Bowden and Tabor, in metal and metal interfaces. They explained that the force of static friction between two sliding surfaces is strongly dependent on the real contact area. Their valuable work is known today as the adhesion wear theory, which is applicable for elastic solids. Adhesion is the force required to separate two bodies in contact. The concept of real contact area was introduced during in this particular theory. The real contact area is the sum of all the large numbers of small regions of the contacts. In this theory, they showed that asperity junctions plastically deform above a critical shear strength, which depends on the adhesive force of the two mating surfaces. They also formulated this simple asperity model of contact based on the Hertzian elastic theory of elastic sliding surfaces. Now, this might be too theoretical, but this particular theory is very applicable even today when it comes to the determination of surface wear properties. They found that the non-linear friction load dependence, this finding contradicted with Amundsen's law. However, both of these laws has application in current scenario. So what is wear? Wear is defined as a process of material removal from the solid surface by means of mechanical, thermal, or chemical action. It has advantages as well as disadvantages. For example, writing with the pencil on a paper is one of the very good example where useful wear comes in picture, whereas wear of machines is not a useful wear. Wear in tribology is the surface damage due to relative motion of two surfaces, due to the bombardment of one surface on the other, or due to the reaction between the two surfaces, or with the surrounding. The science behind this failure is explained by what we call it as wear mechanisms. There are different wear mechanism or different mode of wears. There is adhesive wear, there is a delamination, or we can also call as a sliding wear. There is a fretting wear, abrasive wear, erosive wear, there is a fatigue, and then there's a corrosive wear. Most of the above mentioned wear involves the adhesion mechanism, which results in the wear. The adhesive wear is the most common wear found in the metals and alloys, and is discussed. Let's see if we can have, if we have a little more time, we can discuss about it. Well, during the slide, actually, the material from one sliding surface are transferred to other material surface. I can see that in this particular cartoon, that how actually the debris or the loosened particle forms, because there are two materials involved, and there is a complex process of rolling or during the sliding. That the material, it all again depends on the material properties. and the forces involved and external parameters. For example, if we throw in some corrosive parameters in it, that becomes extremely complicated. But in simple words, if we simplify this, that during sliding, material from one sliding surface are transferred to other material surface due to the adhesive forces between the two surfaces. After that, this transfer stays on the same surface, or it detaches from the surface, and the process continues. And then that's how the debris particle form. And that if this will explain itself, actually analyzing this particle or this debris becomes extremely difficult. Let's talk a little bit about the adhesive wear mechanism. Even today, there are different wear mechanisms reported. Most metals and alloy wear by adhesive interaction between them, as I mentioned. Now, in this particular, this is the theory based on the Bourdon-Tabor theory. When the two sliding surfaces, the shear occurs at the junction. The shear strength of the interface and the metals involved in sliding determines the possibility of the fragmentation. As I mentioned, that Bourdon and Tabor explain 4 different possibilities for shearing to occur. And these 4 possibilities are given in this cartoon. One is when the interface is slightly weaker than both of the mating surfaces, shearing occur at the interface. When the interface is stronger than one of the mating surface and weaker than the other, shearing occurs within the softer metal, and detached segment adhere to the harder side of the metal. When the interface is stronger than that of the mating surface but slightly hardened, then the other severe shearing occur at the softer material, and a significant amount of material transfers to the harder material. The shearing of the harder metals also occurs occasionally. And the 4th scenario is when the interface is significantly stronger than both of the sliding metals, shearing occur at some distance from the interface. In such situation, occurs from both the surfaces, and the surface damage encounters in this particular situation increases as both of the sliding surfaces are damaging. And then there is another theory derived or developed. The damage of the surface also can be determined by this particular theory and combined with Bourdon and Tabor's theory, and this is called the delamination theory. This theory was particularly developed by Professor N.P. Su, which worked at MIT in US. He developed this delamination theory to explain the adhesive wear. Now, just now we saw the 4 different scenarios, and if you apply the delamination theory to adhesive previous situation, and we will know which component and the mechanism of the fragment surface occurs. There occurs when crack form under the surface propagates under continuous loading condition. This leads to surface. The dislocation pile up at a finite distance from the surface, not on the surface. This is very important. So the delamination theory says that the failure actually starts and dislocations piles up at a finite distance from the surface. As the sliding goes on, the voids are formed at the pile-up region, and the rate of void formation is more if the material contains a hard second phase for dislocations to pile against. Basically, if there are again, this is more towards the metallurgical parameters or the microstructural parameters of that particular surface involved. When there are large secondary phase particles in the metal. Now here it's when he says metal, it's not just the pure metals. Actually, we can talk about engineering material. And the voids are formed by the plastic flow of the matrix around the hard particle. Clustering these voids results in a crack, which propagates parallel to the wearing surface or sliding surface. And the separated particles, like a plate-like particles are developed. Now, if you came across the wear debris particles, and if you look at under microscope, you will be able to see the some of the indications that how the sliding wear occur. Then this separated particle, which are kind of a plate-like structure, are generated because of this void formation. Now you can also relate the dislocation theories in material science, to the particular surface damage or the debris formation of these sliding surfaces. Another parameter that we can calculate from this particular area is how much amount of material is owned, or what is the or a rate, actually, in order to determine the rate. But the loss of the material is very important, because that can be related to the other parameters or the action by the engineer, and that is volume of the worm volume by adhesion, and which is given by it is also expressed particularly for adhesive wear, and this was given by Holmes, actually, and it then in Archer in 1953 explained the volume of volume by the adhesion, and that is given by this particular simple formula. The amount of wear is dependent on the load, sliding distance, which is given in this particular formula, and the hardness of the surface. So the material property also plays an important role in determining the volume of the wear volume, actually, and particularly by adhesive mechanism. Wear volume can be given by this particular, and where C is a non-dimensional constant. Now, these parameters can be easily calculated when you conduct the simple friction and wear sliding test, and then we will see if I can have a time, and I can have another couple of slides to determine or to show that how these parameters can be calculated. Well, another important thing is that in adhesive wear, that in order to understand what is going on at the interface, there are two analyses are very important. One is the debris analysis. As I mentioned, that the debris analysis becomes significantly complicated, because during the sliding, there is a lot of things happen. And the second one is the metallurgical analysis of this particular debris particle. I shown these two particular cartoons, actually, just to mention that how detailed debris analysis can be done. The cartoon, if you see the scale of this particular image on the left hand side is around 37 micron. You can see that 37 micron is a pretty small scale, and this particular image was taken by atomic force microscope, scanning a very small own surface, whereas this is also shows the vertical dimension, actually, and that is around 2 micron. That pretty, if you see that, it looks like a very pretty flat, but at very high resolution, as we mentioned very early in this presentation, that there are still irregularities of the surface, even if the surface looks very but by naked eye, when you look at this particular surface, it looks like a pretty smooth surface, but actually it is not. And this particular surface was, this particular sample was carried out with metal on metal contact. And for the same test, the debris formation was analyzed. Particularly if you see that the image on the right hand side is a transmission electron microscopy image, which the scale is around 50 nanometer, and the scale bar is shown. That in this particular case, that the what we can say as the mixing of the materials that are involved in the sliding test can be shown actually at very, very high resolution. Then with these particular tools developed, there is a whole new technology came in picture, and what we call it as the nanotribology. And this particularly study is applicable to very advanced technology, manufacturing technology, particularly the electromechanical system, what we call it as MEMS, meso manufacturing, biotechnology in industry, whereas the tools are advanced actually for the measurement tools. So as you know that the MEMS involve the devices at the micro level, which is mostly made by the micro machining. The nanotechnology has a strong impact on different areas such as, biology, biomedical, computing, communications, and drug delivery. It involves material at very, very small dimensional scale, typically, less than 100 nanometer. And manufacturing at such minute level requires the knowledge of material behavior at that particular length scale, and particularly the surface parameter plays a very important role. And what happens is when it comes to the surface failure at that particular length scale, then it becomes very critical issue. With that, I will like to focus on just one particular tool that can be utilized particularly for nanotribological characterization of the surfaces actually. That is the scanning probe microscope, which is particularly development of this scanning probe microscopy has given a wide channel to study the material behavior at different length scale, particularly for micro and nanometer length scale. There are various techniques developed to measure the mechanical properties of the material at such a very, very small length scaling. These techniques involve surface force measurement. There is another technique, what we call it as the friction force measurement, nano indentation, nano scratching. Scanning probe microscope has obtained huge applications in even in industrial sector, particularly in MEMS application. Scanning probe microscope also open up a research avenue in material science, biology, drug delivery, and many other areas. A scanning probe microscopy is a standard characterization tool being used for polymers and semiconductor studies. There is another tool that is being developed as during this particular application area is the magnetic force microscopy. Particularly magnetic force microscopy is being used mostly at the research level. It has yet to develop the industrial application. And friction force microscopy is nothing but very similar to what we studied about the stylus measurement in one of the slides. But at this particular technique, that both the forces are measured, where in stylus we only measure the surface parameter. In this case, the lateral and vertical force are being measured so that we can also calculate the friction at that particular interface. There is other methods called the nano indentation method, which is very similar to what we have the hardness measurement at the conventional level, but it is very precise and the indentation is very, very small. So we get the most fundamental parameters of the surface measurement. In order to study the nanotribology, the atomic force microscope and the friction force microscope is considered as one of the suitable equipment. AFM has emerged as the powerful tool to study the surface properties, as I mentioned, at different length scale. The friction force microscope or AFM, there is a scratch test also that is being considered as one of the important tool in tribological study. The study of nanotribology is important in various fields called, say biomedical applications in particularly the study of ultra high molecular weight polyethylene, where the nanotribological characterization plays a very significant role, because this particular polymer is being used in the application of total hip and knee joint applications. Now let me discuss just a little bit about this particular two images. These two images are taken by atomic force microscope, and as I mentioned that when we do the friction force microscope, so we also measure both the forces. Now both the images, if you look at that on the right hand side, it shows the surface topological characteristic of the surface at very, very high resolution. If you see that the length of this particular image is only 48 micron. And so the image is 48 micron by 48, around 40, 49 or 50 micron, you can say, by 50 micron area is being scanned, and that particular area, how the friction changes over that particular cross section is also given on the right hand side image. This is the atomic friction force microscopy image, that particular very, very particular space, how the friction or the surface behavior of that particular surface varies actually based on the governing all the law of physics. If you see that the graph or the color change on the right hand side image is shown by the voltage, micro voltage, and then this micro voltage can be connected with the parameter of the friction. And in general, we can say that the variation of the friction on that own surface is very interesting. And this application of this particular study, you can think about how we can go on the MEMS devices and their failure. Now this was, I wanted to conclude, but I forgot to make the slide for the conclusion. But this is where the tribological features or the tribological current status is. And with this, I would like to stop my presentation. I think I might have used a very less time, but I'm open for the questions, if you have any, or I will be also available at this particular email address. That if you have any other question that you can ask about, not just for the research, but any assistance you needed in your career, I would be happy to connect with you. With that, I will hand over this to the organizers.
Yes, sir. Thank you for your nice and informative session. Initially, you are saying that we are talking about the basic thing for the tribology and its impact on energy and sustainability. But I think you covered all the topic in the very deep manner. You already discussed the basic thing with some examples, so it will be helpful for the researcher also. Most of the time, what happened, the researcher, they did some experiment, but they don't know which type of characterization is useful for that particular application. So I think from your presentation, most of the researcher, they clear some ideas related to the characterizations, test method, and all these things. So I would like to request the participant, if you have any question or discussion with Dr. Sudeep Ingole. Now the forum is open for all. So please unmute your mic and you can ask the question.
So, good evening, sir. I am Dr. Manish, working in CPET Jaipur as assistant professor. Sir, my question is regarding, I have shown a slide, there is various type of wear. Hello, sir.
Yes, I'm listening. Go ahead, Manish.
So where I find mostly the fatigue wear?
Oh, your question is, where do you find the fatigue wear? Is that right?
Yeah.
Right.
Yeah.
So particularly for fatigue to happen, actually, that there is one of the most important loading condition is the cyclic loading condition.
Yeah, that only name the given of fatigue.
Pardon
As
me?
practical application, I am asking regarding the practical. That's why it is given the fatigue wear. Without fatigue loading, there will be no fatigue.
Right. Let me give you very layman's answer for this particular question. Let's say a person has an automobile, a car, right? And the person does not change the oil in it. Over a period of time, what will happen? What will happen is, because of the sliding condition at the interfaces changes and the engine start vibrating, right? And this vibration can lead to, I'm just giving a very layman's answer. There could be a lot of other industrial applications where the fatigue wear comes in picture. And then what happens is that the cyclic loading start coming. When the vibration comes in picture, they say that if you are late on your oil changes, or if you are lazy on oil changes, it is not just the oil change that you are responsible for, but you will be responsible for all other maintenance issues in the automobile, because that particular cyclic loading can lead to many different failures. Well, coming back to the scientific way of where the fatigue wear occurs, think about particularly in engine applications, or anywhere engineering application where the cyclic load. Well, this cyclic load is not necessarily like a regular cycle. It could be just because of the vibration, or if it's a locomotive, then there is because of the continuous motion that the cyclic loading can happen. For example, think about aerospace industry. There are a lot of failures that have happened because of the fatigue loading. Now I'm talking about fatigue fracture, the fracture at the interface because of the fatigue loading, right? So there is a fatigue fracture for the material is one aspect, and the fatigue wear because of the cyclic loading is a different aspect, right?
Yeah.
The fatigue failure could be just the material failure, but the fatigue wear is result of the cyclic loading. Now the cyclic loading is not just because of the sliding interface, but it could come from the external parameters also. Now you might have heard about there is a one type of friction behavior, what we call it as a stick slip friction.
Yeah.
Right. So you take like nowadays there are no chalkboards and blackboards, but if you take a chalk, right, and you hold it in a certain angle and you try to write with that particular chalk, you will see that a very simple stick slip friction occurs, right? And if you consider at a micro level and continuous manner, right, particularly when the sliding condition goes towards the dry sliding conditions, or when the hydrodynamic layer breaks, you might be knowing the Strybeck curve, right? So if you move towards the dry sliding conditions, then the stick slip might happen, or the dry sliding friction can happen, and that could lead to the fatigue failure of the surface. Is that answer your question?
Yeah. Okay, thank you, sir.
Thank you, Manish, for the question.
Anyone participants? If you have any question, discussion.
Sir, I have one more question regarding at nano level.
Go ahead, Manish, go ahead.
Sir, what is the parameter to measure the wear basically? Because you have shown various parameters. What are the parameters, at micro nano levels, to describe the wear?
Or in order to measure the wear.
Yeah. At
Right.
nano level,
So let me. Sure. At the nano level, actually, the parameters, those are going particularly not by sliding wear, actually, because it's the sliding wear tests are very difficult to monitor. There are like a couple of tests those are developed that are can be converted into quantitative parameters. Those two tests at nano level are the indentation test, nano indentation, what we call. And then there is another test, what we call as the scratch test. It is called the nano scratch test. And then the parameters involved can be the deformation of the material. We can also calculate the force. We can also calculate the depth of the material. We can also, based on that, we can calculate the volume. And these are the standard tests being available for particularly at the nanometer scale.
Good. Thank you, sir.
Participants, if you have any question.
Sir, so my request, will you share the slide to all of us?
Yes.
Certainly, I will share the PDF of the slides. I will send it to the organizer, and then that can be
Thank you, sir.
distributed.
Sudeep sir, I have one question.
Sure. Yeah.
Suppose someone want to work on the knee joint for the biological material. So which type of test we need to conduct?
You mean for the hip and knee joint applications?
Yes, yes.
Okay. Very good question. Now, what happens is when you take the laboratory-based test, like a standard tribological test, we have like a sliding test, right? Sliding test. When you take like these tests are environment, right? So there are certain new tests are developed actually related to the hip and knee joint applications. But if we immediately want to start the research in hip and knee joint application, so there are other parameters are very important that need to be considered. One is the surface properties and the ability of those surfaces based on the manufacturing technique to produce these surface features. Like, for example, how smooth the surface can be, right? Or if there is any surface asperities are produced or something like that. That factor, that is one component of it. And then if we have the manufacturing method, the material system that can produce the reliable results, then we can say that okay, this material system has the potential to be applicable in the hip and knee joint application. Then the second parameter comes is the biocompatibility of the material. Because I did not show that slide because I did not wanted to make it too scientific, but there are studies actually that even the best material that is being developed now for the hip and knee joint application, the failure of those material is so serious that, for example, the hip and knee joint replacement, consider like a knee joint replacement in a patient, but over a period of time, the wear of that knee joint, the particles, debris formed, as we see that the wear can happen even at an atomic level or at a nanometer length scale. In some of the patients, that the debris particles from their knee joint were found elsewhere in their body. For example, the spleen of the body is what we call it as the recycling bin or something like that, right? And it tried to collect all the debris from the body, like unnecessary. And it was found that some of the material that is, related to the joint material are found in their spleen in the patients, in real patients. I'm talking about real patients. Now, let me come to another serious study. In one of the studies, the implant material, some of the fractions actually, the what we call say that stresses of the material that is being used, that material is being used as an implant in the patient's body, were found in their brain. Now you can think about how serious it could be, right? Yes. So these parameters are very important to study. So even if we start with a very basic research for biocompatibility, or you can also, there's a very standard method being developed, what we call it as a biotribology. We can take the standard test, right, and then simulate it in a bio condition. For example, there might be possibility that we can simulate the bio-lubrication. You can also get the synovial fluid generated. Like, nowadays there are injections are available that the synovial fluid can be injected into the knee joint application as a lubricant, right?
Yes,
so you can use some of those, and you can use it very simple, and you can get very important information through that, right? When it comes to the simulation of actually hip and knee joint in the laboratory, and simulating those conditions, and then it is up to the researchers, how they can design their own tool. So the standards are not yet developed to the level that those can be initiate the actual loading conditions of the hip and knee, like any biological joints actually. Yeah, but you can approach to it.
So that's why I think most of the researchers, they are using the pin on disc type of the testing and all these things, because the standard test trick for the biological application, I think, not available till then.
Right, exactly. But but you can simulate some of the conditions.
Okay.
Right, you can consider, because the wear of the material could be very, very relatable, right? And then based on that, what is the debris formation during that sliding condition, it could be related. But then you can also throw in some biotribological parameters, try to see if the synovial fluid has any effect on it. Those parameters can be, but there are some of the hip and knee joint implant manufacturing companies have developed their own tests actually.
Okay.
And then they test, because what happens is, in order to measure the longevity of the actual hip and the joint that is being developed, they need to still study those joints. So they have some kind of a simulated test, to measure the number of cycles, how many cycles this material can last. Here, what happens is, particularly hip and knee joint application, first failure is that's all. That means like you cannot go beyond that. So the acceptability of any surface damages, it's very, very negligible, very less actually. For example, in engine application, you can say, without oil, maybe you can drive a car a couple of 100 kilometers, and then you change the oil, and then surface is still forgivable little bit, right? Whereas in knee and hip and knee joint application, it will be very difficult, because the knee can relate to many different complications in the human body.
Yes, sir. Thank you for your nicely explanation question. Now I request to participants, if you have any question, please ask. Otherwise, we will stop for today's session. Okay, please ask the question. Unmute yourself and please ask.
Someone, Shefal, want to ask.
Shefal, yes.
Hello, sir.
Yes, sir. Manoj Kumar Kate. Yeah, yes, sir.
I am Manoj Kate from Nutan Maharashtra Engineering College. First of all, thanks, sir, for sparing time for this session, and your session is very
Hello, Manoj.
Informative, sir. Hello. And my question is related to my research work. I am doing research in wire EDM process parameter optimization. And if we consider the surface finish as a study parameter, which type of parameters we need to consider for surface finishing of wire EDM process? Am I audible, sir?
Yeah, you are audible. I couldn't get your first parameter. What work are you doing? Working on? You said your
process parameter optimization of wire EDM machining.
Oh, wire EDM.
Yeah.
Oh, okay.
Electro discharge machining process.
Yeah. So it's a electrical discharge machining, right?
Yeah.
So in yes, very, very interesting. Yeah. So, well, what happens is, first, most basic thing in EDM, right, or electrical discharge machining, is the material removal, right? And the material removal is nothing but it's a result of Basically, it's a result of friction. But in wire EDM, what happens is you're also using the electrical energy, right? So there the primary parameters is comes in pictures from the electrical voltage point of view, right? So what range do you get into in terms of the voltages? Do you get into at the interface wire and the material interface? Do you go into the plasma region, or do you go into the mechanical, just the spark, like a high voltage spark, and then it increases because of the resistance of the material, it increases the temperature, and then you end up removal of the material? Because what happens in that term, in that case, you need to look into the wire itself, actually the surface properties of the wire, right? So the basic thing is that you can relate many of the parameters based on the surface roughness of the wire, right? So that is the most basic parameter that can be considered, but again, it depends on the mechanism of particular mechanism you're focusing on.
Okay. Okay, sir. Thank you.
Shepa, I think you are having one question. No? You are raising the hand. Shepa, please.
I think no questions, sir. So we'll end the session. Thank you very much, sir. Dr. Sudeep Ingole. You have given the very nice session, sir, which will definitely help for all the participants for their further research work, sir. In spite of, again, a busy schedule, right now I think it's early morning in the USA. So sir has responded for everything, of which we requested and sent the mail to him. Thank you very much, sir, being a part of this FDP, sir. Definitely in further also we'll have the collaboration with you and we will work together, sir.
Certainly. I will be also presenting in one of the other days, I believe. Sure. So with that, should I disconnect?
Yes, sir. Yes, sir. You can, sir. So participants, now we are end of the second session. Thank you all the participants for showing your interest for this FDP. So like today, tomorrow also we have the second day session, which will start at exactly 6 o'clock, 6 to 7:30 and 7:30 to 9 p.m. So I request all the participants, please do join before 6 p.m. so that we can start the session exactly at 6 o'clock. Tomorrow we have again different topics to discuss. So we have the very good experts from the again from the reputed institutes as well as from the industry point. And regarding the feedback, we'll share the feedback link to the WhatsApp by tomorrow. If those people, those who are not connected to this meet, please inform to all your colleagues and the friends so that we can get the better, good response for the upcoming sessions. Thank you one and all. Good night. Thank you, sir. Okay. Stop recording.